We can.
It should be, yeah. Slides. If they do the entire, I think they have to go Shall I ask the students if there's someone who wants to
But they will have to be there.
Yeah, or they can send it by email maybe.
Okay.
That's what I did yesterday.
Okay.
I'm not sure if it's too complicated.
Yeah. I was wondering, what do you think of still try to gather this small discussion at the end for the CD question, take preparation a little bit.
But we have like another question.
Yeah, after
Maybe we can also.
Yeah. Okay. Yeah. We'll see how because I think we're gonna probably start in 5 minutes. So probably,
Yeah, we are already a bit late.
yeah, just this morning. Excuse me. I know, but this microphone.
It should be. You need to press the red button. We had it yesterday too, like this.
Discuss it. I'm sure we can arrange.
Yeah, I think it's fine. Maybe we are even late always. Maybe we just also program. It's on now. Yep. Shall I start? Do you want to say?
As you wish.
Oh, as you wish.
Okay, I can do the first, you do the second.
Now I can.
Okay, we're gonna start. So welcome everyone to the first volcano session. So there is 3 volcano sessions with INSAR application. So we're gonna start today with Suzy Ebmeyer, that's gonna present interaction of volcanoes in Galapagos. So because we have a bit of time, because one speaker canceled the last one, so we have gonna have like the talk about 20 minutes, and then we have some time for the question, so the speaker can take 20 minutes, and then I can give you a 2 minutes warning. Yeah.
Is the last one Biran?
No, after him. After him, we have from 12:30 to 12:50 before the lunch. We have some time, so we can discuss about like open question and seat question, but we can also have more time for the speaker to give their presentation. Okay, Suzy, the floor is yours.
Okay, great. I say it feels really nice to give a fringe presentation in here instead of an undergraduate lecture. It's definitely a much nicer use of the room. And I don't have to monitor everyone's phone use, make sure people are paying attention and do the follow-up exercise. So this is lovely. There are also more of you than we have undergraduate geophysicists, so that's good too. Right, so I'm presenting some work from one of my PhD students from Owen Redden on the deformation of the Western Galapagos. The other thing that's particularly nice about being able to present this at an ESA meeting is that this is work that was actually quite directly funded by ESA. So it went into a proposal that I made for a Living Planet Fellowship all the way back in 2014. I had to go and look it up to try and apply independent component analysis to Galapagos deformation. And then for various reasons, because the time series were quite short and because I got distracted by other things, it never really happened then. And Owen has incorporated it into his PhD thesis as his kind of central chapter. So Owen is at the rugby in France at the moment, so he's not here to present it himself. So I'm going to try and do his work justice today. So the Galapagos is a really beautiful place to work on INSAR. You have very high magnitude signals. You have exceptionally high rates of eruption, rates of intrusion, and beautiful geodetic expression across all the islands, and they're all so amazingly coherent. There are 6 volcanoes in the Western Galapagos, of which 5 have had multiple 20th century eruptions. And the fact that the crust in the Galapagos is relatively thin means that you have multiple points of magma ascent within relatively close proximity, so within 100 kilometers of each other. So the figures here just show the 20th century eruption at the Western Galapagos volcanoes and a selection of the more recent effusive events on the right there. So the Galapagos has been incredibly well studied by this community, by people using INSAR, including several people in the room. So if your paper is not on this slide, then apologies. But a lot of this work has focused on either studies that essentially look at long-term displacements over decades, or they focused really on eruptive events. And that's understandable because the eruptions in the Galapagos are spectacular. There are also these amazingly large intrusions, especially associated with the larger calderas like at Sierra Negra. But the approach that we've taken has been to try and look at complete time series of deformation in the Galapagos with a focus on the inter-eruptive periods rather than the eruptive events and major intrusions alone. So this is a summary of what we've discerned at a kind of like first pass level geodetically from looking at Galapagos volcanoes. So that incorporates historical observations made by other people, mostly from elastic half-space modeling, and Owen's modeling of sources in the Sentinel era. And all of the volcanoes in this group have geodetic evidence of relatively shallow reservoirs, so from 2 to 3 kilometers depth, and several also have evidence of larger storage zones at around 5 kilometers. And we're somewhat limited at looking at deeper depths in the Galapagos because of the size of the islands themselves. So from adding in the Sentinel data and looking at the more recent time series, that you can do a couple of things that hasn't been possible before in the Galapagos just because of the temporal resolution of the data sets. But the first kind of baseline observation that Owen's been able to make from this work has been that actually the magmatic sources in the Galapagos are pretty consistent. People do tend to find similar storage zones to within error using a variety of different modeling approaches, and you have kind of clusters in the location and the volumes of the magma storage areas that have been found using INSAR. The cartoon on the right of this slide summarizes what other people have, the way that other people have described magmatic systems in the Galapagos, and Owen's findings from the Sentinel data really fit into that relatively well. There don't seem to be any major changes in the most recent time period. So our focus has really been on trying to ask the question of what do the relationship between the deformation patterns at the volcanoes actually tell us about Galapagos volcanism? So can we use it as a window on deeper processes? And the approach that we've taken to that is looking at the time series and trying to look for similarities between them. So this is the main figure with fringes in the fringe presentation. This is actually the descending displacements for the Galapagos since 2017. And you can see the time series on the left have a lot of structures associated with the eruptions. Fernandina eruptions are marked there in red. There was a major eruption of Sierra Negra, which is marked in the blue hash blocks, and then a couple of intrusive episodes as well. To get everybody's eye in, I would like to draw your attention to a couple of major events. So Fernandina and Sierra Negra erupted in relatively quick succession in 2018. That's in that pink box there. And you can see already just by looking at the time series, there are some common features in the displacements that span this period. So even though the eruptions were at the Fernandina and Sierra Negra volcanoes, you can see a change in the displacement direction at Darwin, and something similar at Cerro Azul. And you can see something, I think, even more spectacular before the Wolf eruption of 2020, where you have a change in the direction of displacement at Darwin, where there was no eruptive activity and no evidence of any unrest, and also at Alcedo, which are volcanoes which are really quite a long distance away from the eruption that took place at Wolf. So that's the kind of first order observation. It isn't a new one. Other people have pointed this out before. So this is from Scott Baker's thesis in 2012. So he identified 4 periods of commonality in deformation trends and also in other expressions of unrest, so seismicity, during the period from 2020 to 2006 to 2009, so the ERS and NVSAD era. And we started off with the approach of trying to see which pairs of volcanoes seem to have correlations in their deformation, the idea being it might be a kind of pairwise correlation, because that seemed to be what Scott's observations showed. So he saw similarities between the Fernandina and Alcedo deformation. So this grid shows all of the volcanoes. It shows particular episodes that have been identified as having kind of some apparent correlation in unrest, with a symbol representing when those have taken place. And you can see from Scott's earlier work, pink circles, that really seem to be a kind of a pairwise phenomenon. And we tried to take a similar approach, and essentially we ended up having a symbol in every single box, because when you started looking into it, you could kind of identify matching details of the time series between all of the different pairs of volcanoes. So that really allowed us to make a more robust investigation of whether this correlation is real and reliable, and you can actually use it to understand something about the geophysics of the system. So the first approach we used to do this was straightforward identification of turning points, looking for places where your gradient was 0, so you switched from uplift to subsidence or vice versa, or you had a major rate change on filtered time series. And hopefully the kind of the red and gray bars on this image match where your eye would naturally pick out the turning points in the time series. Just to get your eye in, those pink boxes are the same as the ones I showed before. So the first one refers to the Fernandina and Sierra Negra events in 2018, and the second one is the run-up to the Wolf 2022 eruption. The next approach was using windowed paired correlation analysis. So that's all of the, every line on the y-axis here is a different pair of volcanoes. That's for both the ascending and the descending data sets. The blue and the red boxes here show where you have correlation values that exceed 0.9, with red being a positive correlation and blue being a negative correlation. And you can see you have these quite kind of satisfying clusters through time in these boxes that show you have episodes of enhanced correlation between different pairs of volcanoes that seem to occur at the same time. And then this last method is temporal independent component analysis. So essentially that's an approach which allows you to break random variable down into different components where their independence is maximized. So in this case, we've applied that temporally. So we've tried to maximize the independence of the temporal components. The figure here shows Owen's approach to downsampling the Galapagos. So he had about 8,000 time series. He took those at a spatial resolution which is a little bit higher around the calderas, and otherwise just an even grid across the rest of the islands. And then he did temporal ICA on those 8,000 time series for the different time periods and time periods of moving windows across the whole Sentinel dataset. Then we used the clustering approach to looking at the retrieved components to test their significance. But what was really useful about this is that you get temporally independent components which essentially look like time series. And then you get a mixing matrix which gives you the relative strength of those time series in all the different locations around the Galapagos. So what the results I'm going to show you really use those maps. So for this first period that I pointed out before, the 2018 events involving Fernandina and Sierra Negra, you can see we have a temporal component which has a turning point during the Sierra Negra eruption, and that has a high weighting over Sierra Negra itself, but also over all of the other volcanoes. It's non-zero at every single other volcano in the Western Galapagos, although it's particularly strong here in Fernandina. And I think even more impressively, you have a temporal component which seems to match precisely the timing of the Wolf eruption, which is weighted strongly at Fernandina and Sierra Negra, and to some extent at Cerro Azul as well. So I think this is a really kind of nice test of the robustness of these correlations. So the kind of the obvious question to this is, well, couldn't this just be a processing artifact? Couldn't this just be because you've used a common reference pixel, or could it be a kind of common atmospheric feature, or kind of something to do with a hydrothermal system? And that's something we worried about and thought about quite a bit. So we kind of tested the possibility of it being being to do with your choice of reference pixel. You can see those are actually plotted in the time series in panel A there. And also played with atmospheric corrections and see if there was any way that we could try and get similar results from something to do with the processing. And we're pretty confident that's not the case. The next possibility is that it's something to do with static stress interactions. These are very active systems. Couldn't it just be that an eruption at Sierra Negra was affecting the neighboring systems at Cerro Azul? And we also don't think that's convincing. It's certainly not enough to explain the degree of correlation between the time series. For example, this very large event at Sierra Negra in 2018, the dilational strain that it produced didn't really extend very much further than the neighboring volcanoes. It certainly wouldn't have affected Wolf. So that seems a kind of unlikely scenario. We also thought a little bit about whether there was some sort of volume changes that could be happening somewhere we don't see them. So for example, you can see beneath the channel between Fernandina and Isabella, but we don't really see any evidence for that in the data, and there aren't any kind of culprit events that seem like it could have caused this sort of static stress change. So that leaves us with shallow hydraulic connections, which I think if they existed in the Galapagos, we would see them geodetically because the coherence is really good. And where there is lateral movement in the Galapagos, it produces amazing deformation. So I think that one's also not plausible, which leaves us the possibility of deeper connections between magma supplies, which is what we think that is the right answer here. So to summarize what this looks like, we have correlations in displacement between all of the pairs of the 6 different volcanoes. These are during eruptive episodes that last days to weeks, but they're also, kind of more interestingly, in interruptive periods over last weeks to years. We have trends between episodes of general uplift in subsidence, turning points in the same place. One thing that people have sometimes asked about this as well, if you have a couple of monotonic processes, obviously they'll be correlated because they're both uplifting, they'll look like they're correlated, which is true. But what we also see here is correlations in the small time series variations that are pulled out by the temporal ICA and the correlation analysis. So it's more than just that. So one of the things that Owen worked on recently was estimating the probability of 2 volcanoes having a major change in their deformation rate at random at a particular time, which is based on the idea, it's based on the number of major changes you have over a particular period, and then just assuming that they're randomly distributed, which they're not actually. But if they were, we would expect that probability to be less than 1%. And similarly, the probability of Sierra Negra and Fernandina erupting within a 6-month window, based on their 20th century eruption rate, seems to be less than a percentage as well. So we're pretty convinced that these correlations are real and they mean something. Oh, sorry, so then we started to look at what we could link these correlations to, what other factors we could discern from the geodetic data that might be linked to it. And the obvious place to start is looking at the intrusive flux. So the left-hand side of this panel here is from Marco's work, where he looked at the cumulative volume change that was intruded into the Western Galapagos Islands, and Owen has updated this with the Sentinel data. And we can see that there's a temporal variation in the total intrusive flux, but also a variation in the share of magma supplied to the different volcanoes in the Galapagos through time, which is kind of consistent with historical observations of clustering in the eruptions that take place there, and this idea of magmatic flushing, which comes from the petrology in the Galapagos. So if we compare the correlation count, so that's the number of highly correlated pairs of time series, to the intrusive flux, we find we have particularly high correlation counts during episodes of very high, very high rate intrusion. So that's, I think it's easiest to see again in 2018 around the Sierra Negra eruption, but also right at the end of our time series there, you can see there's kind of an uptick at the end associated with the Wolf eruption, both in the positive correlation count and the negative correlation count. So that leaves us with Sorry, this actually looks okay on the speaker ready computer, but there we go. um, so the majority of the strong correlations between pairs of displacements were episodes of uplift at multiple systems, and they're correlated with high supply. And that's something that's kind of conceptually straightforward, right? It kind of makes sense. You have more magma coming into the base of these systems and more magma entering the shallow system, you have a correlated uplift. You'd have something similar with positive correlation from subsidence during an episode of lowered supply into the transcrustal magmatic zones, essentially just because you're entering a period of cooling and less magma going into the shallow system. In some ways more interesting, you have negatively correlated displacements, which we had at a few points during the time series we've looked at. And they were obviously associated with major eruptions. Anything that perturbs the system in a top-down sort of way instead of a bottom-up way could have that impact. But also we think in variations in the supply of magma from the melt zone into the shallow crust. So that could be because, for example, of enhanced melt production beneath one volcano, or it could be because of a pathway opening, and you can't see that from the data directly. So the question then is, how deep are the connections between these volcanoes? So there's a couple of bits of evidence here. So over the last 10,000 years, the lava compositions at the Galapagos volcanoes are distinctive. So it looks like they're sampling geochemically different parts of the Galapagos plume. So that puts kind of a floor on the potential depth of our source of interaction. They're obviously above that. And we don't see any geodetic evidence of lateral transfer. So that's a kind of upper limit. They have to be below that. And then there's quite a big zone in between those two limits. But by analogy, at Hawaii, there's been recent evidence of an asthenospheric melt layer from seismic imaging. And it's also been hypothesized from other people from earlier work. And something similar has also been proposed to lie under El Hierro in the Canary Islands. So that seems like it might also be a plausible scenario for the Galapagos Islands too. So that leaves us with a kind of overall picture of the Galapagos volcanism that looks something like this, with some question marks and with some kind of uncertainty on some of the structures. But we know we've got distinct vertically extensive subvolcanic magmatic zones underneath the volcanoes. We know there is some zone where they can interact with each other, which we think is below crustal depths, because that's been seen in other places. And we know that each volcano taps an isotopically distinct source of melt from deeper. So that's our conceptual model that comes from looking at interactions in the time series. So I'll stop there. I think I've got over by a couple of minutes. Yeah, okay. So we see consistent correlations in displacements in the Western Galapagos, and these are especially strong during episodes of heightened magmatic flux into the shallow crust. There are correlations in this displacement, but with distinct isotopic signatures, which suggests you have connections at depth, but not at the source of the melt. And I think this is a kind of nice illustration of what you can do by looking at time series over a much bigger area at neighboring volcanoes, at clustering volcanoes, rather than treating them as isolated events. But I think we can learn a lot more by taking this approach than by looking at systems in isolation. I think that's me. Thanks, Fabian.
So we have time for a couple of questions. We have a microphone.
I can hear if you shout.
So my question is, so I noticed that for like the 2018 Sierra Negra eruption, it looks like there's 6 to 8 meters of subsidence that happened, and you're showing something like on the order of a meter. So does that, I guess I don't know enough about the ICA analysis to know whether, does that affect any of the connections with some of the other time series? In other words, if there's a disproportionate signal in that wasn't captured, does that affect things, or is it really just the timing that's important and not the relative magnitude?
I mean, ideally, it should really just be the timing and the shape of the time series that would be important. Of course, in practice, Sierra Negra dominates everything else happening because the magnitude is so much larger. So the first step doing the ICA is a principal component analysis, and you have a choice to make as to how many components that you then go on to retrieve. So if you think that one of the components might be relatively low variance compared to the rest of the system, it's going to be easy to lose that if you get that number wrong. But the answer is, I mean, I think the correlations are robust in spite of Sierra Negra being the biggest, because it's all normalized before you do the analysis. Oh, sorry, Patty. Yeah.
Well, thanks. I think there are some examples of this also in Iceland over very long distances. You may have heard of them, between like the onset of the Krabla fires and then subsidence onset in Askja, 80 kilometers away. But the question was more about the exact timing of when you start to see these changes. Can you really see like a wave from north to south, for example, after the Serra? Something that that the ones that are closer see the change earlier than those that are further away?
No, it's a good question, and we looked for that. But the answer is no, we don't really see that. And I'm, to be honest, I'm not completely sure whether that's to do with the resolution of our time series, or perhaps it's also affected by other modifying processes that affect the timing of the change in pressure at the shallow systems. And I think this is one of the more puzzling things about the answer that we've come up with, is that from the point of view of our data set, these things kind of look like the correlations are simultaneous. So we tried to solve for a lag time as well, and we find the lag time to our best guess is 0, which seems kind of improbable. But I wonder if that might just be the result of the kind of data uncertainty rather than something we can completely trust. I mean, it'd be really nice to be able to do this on a GPS time series and see if you got a similar result.
Okay, thank you. Maybe, one last question.
Quick one.
Please use the microphone. I think otherwise it's not online.
Quick one.
Okay, well, very interesting. You said something that the random probability for Sierra Negra to erupt after Fernandina eruption is 6%.
Less than 1%, I think it was.
But so Fernandina, the number doesn't look right to me. Fernandina is erupting every 2-3 years or 4 years or something like that. Then the probability should be much higher, isn't it? The random probability.
Yeah, I mean, this is
That's how you
it's a
calculate
slightly
it.
rough back of the envelope calculation, and obviously it depends on the window over which you take the number of eruptions. Depends over the time interval that you look and take that number from. I think that calculation came from the window, the 20th century eruption rate. And it will vary whether if you pick a shorter time window or a longer one. I think there's a problem with that approach anyway, in that we don't really expect the eruptions to be randomly distributed through time. So it's essentially just to give a kind of to test the confidence that we have in the time series correlating at random.
Okay, thank you.
Thank you. We move on to the next presenter, who is Adriano Nugele from Faust, and he will talk about Askja Volcano.
Okay. Hello, everybody. Thank you for coming. I'm Adriano, and today I will show you some nice interferograms that show the interaction between magma chamber and the caldera ring fault at the Askja caldera, at Askja volcano in Iceland. So caldera forms after a big eruption or a big magmatic intrusion that empty the magma chamber, and the roof block collapse along the ring faults, generating the characteristic caldera depression. further pressure change inside the magma chamber can trigger some slip along the ring faults, generating some peculiar deformation pattern. In particular, you can see again. Sorry. How it's working. Okay. You can see that the deformation is constrained inside the caldera, and in general there are larger deformation nearby the rim. Furthermore, when the magma chamber is interacting differently with different parts of the ring fault, can generate asymmetrical displacement, as here during the 2014 collapse at Bardabunga. Okay. So Aschia is located in the North Volcanic Zone in the Icelandic Rift. It consists of a central volcano with 3 calderas and erupted fissure worm in the north and southwest. Last eruption occurred in 1961 in this area, with the lava flowing toward the west. After this episode, the volcanic system has been really well monitored, and in particular, we have geodetic data since 1966. This data shows that between 1970 and 1973, the caldera was uplifting, and then it started to subside with a decreasing rate. INSAR data shows that the deformation was mainly constrained inside the caldera, but there was also some deformation in the erupted swarm area in the north. The inversion of these data suggests the presence of a shallow magma chamber at 3 kilometer depth. However, part of the deformation was not, they were not able to model it, so it's explained with the opening of the ring. The deformation, the subsidence continued until 2021, as highlighted by GPS data, but in August 2021, the situation completely changed, so it started to uplift with a really fast rate, about 60 centimeters per year during 3 months, more or less. And then the uplift was still ongoing and is more or less constant with 30 centimeters per year. In the same period, the seismicity started to increase again for 3 months until November. The seismicity was quite high, below the lake. And then it went back to the background level. For this study, we used the Sentinel-1 data. The area is covered by 4 tracks, 2 in ascending and 2 in descending. Unfortunately, most of the year, Aschia is covered by ice or snow, so we could use only images acquired between July, August, and the beginning of September. Finally, some fringes. I will show you the arrow here, show the temporal evolution. On the first line, we have the filtered interferogram and the corresponding deformation map on the second line. The first interferogram spanned 5 years between July 2016 and July 2021. It shows movement away from the satellite, so consistent with subsidence. The second one is a really short interferogram, so 42 days, and it shows the change on the deformation pattern. So now it's in uplift, and in less than 2 months, it recovered completely the deformation produced during the previous 5 years. The third interferogram is a 1 year time span, and it covered the period between September 2021 and September 2022. 29 centimeters of movement toward the satellite, so again uplift. And the last interferogram, again, September 2022 and of August 2023. and again 29 centimeter of uplift. These two last interferogram are really consistent with the linear deformation pattern observed with the GPSC. So, few things to notice. So the deformation is merely constrained inside the caldera, and it follows the structure observed at the surface. Another thing to notice is that the deformation pattern between the subsidence and the uplift is almost the same, and the maximum uplift is shifted north for the subsidence of 100 meters. So for us, our interpretation is that the source of the two deformation is the same. As I was saying, there are 4 orbits, so we process the deformation time series, and here I'm showing the deformation map for the period between 2017 and 2021. All the 4 orbits show movement away from the satellite. That is consistent with subsidence. Instead, for the deformation map between 2021 and 2022, we have movement toward the satellite, consistent with that. If we compare the 2 ascending orbits and the 2 descending orbits, we can see that the deformation is exactly the same. If we compare instead the deformation between one ascending and one descending, we can see that in general the ascending, the amplitude of the ascending is larger than the descending, and the deformation is slightly different. This is due to the different looking geometry, but it means also that there is an horizontal component in the displacement. So we combine the one ascending and one descending orbit to get the vertical and nearly east-west component for the subsidence period and the uplift period, more or less 14 centimeters of subsidence during 4 years, and 45 centimeters of uplift in 1 year. For the horizontal component, here you can see probably the 2 lobes moving toward the center of the caldera. This part, so our reference point is on North American plate fixed. So this part is a Eurasian plate moving toward the east. And probably you can see here some deformation that Sigurjon Johnson will show better this afternoon. This is instead the deformation during the uplift period, and you have the 2 lobes moving apart. We are talking about 20 centimeters per each lobe. We extracted we extracted this profile for the vertical component. I will talk only about the first one, that is the one in the north. So 4 centimeters of subsidence in the eruptive fissure area during the period 2017-2021, and 3 centimeters during the period 2021-2022, meaning that there is an acceleration in the deformation inside the rift during the unrest habitat. So there is possibly an interaction between the magmatic surf of Asia and the rift extension. We move now to the deformation surf. I tried to model the deformation with one surf. In this case is one seal. We use analytical model, and we inverted the 4 orbit. I'm showing only 2. So the field is located, the center of the field is located below the wing, let's say the center of Astia caldera, and is on the shore of the lake. It's located at 2.6 kilometers, that is close by the 3 kilometers observed for the subsidence. We could explain only between the 55 and 71% of the total displacement observed, so not so much. And if we look at the residual, in general, we have an overestimation of the maximum displacement and an overestimation of the signal nearby the ring fault. Yes, and instead is the opposite in the middle of the caldera. I will talk about this part later. So, since the deformation obtained with only the seal was not enough, we tried to model the interaction between the seal and the caldera ring fault. For this, we used the boundary element models, and we implemented this on the BIT software, Bayesian earthquake analysis tool. So in this case, the seal is inflating and is pushing up the ring faults. Depending on the position of the seal with respect to the ring fault, the nodes of the ring faults move differently. What we obtained is a deformation surf, deformation pattern that is asymmetric and is quite similar to the one observed with infrared data for both ascending and descending orbit. We improved the variance reduction. Now we are between 74 and 90%. If we look at the residual, for the descending, they are really well distributed and quite small. Instead, for the ascending, we still have some problems. Okay, this part is located above a low velocity seismic zone. And this area is interpreted with the presence of fluids. So probably the heterogeneities that in our model cannot be introduced. Here, only a quick comparison between the vertical displacement observed modeled with the seal and modeled with the seal and ring fault. You can see that the seal overestimates the displacement. Instead, the ring fault and the seal fit better with the results. Another thing to notice is that here, that corresponds to this zone, there is an anomaly in the deformation trend. This area is close by the ring fault of Ostiwatne caldera, and there are also eruptive fissures. So our interpretation is that these features can interact with, can produce part of the deformation. So just to conclude, okay, with INSAR we could observe the 2016-2021 subsidence, and the rate was still decreasing comparing with the previous geodetic results. We could observe the 2021-2022 uplift, and we could see that the uplift is still ongoing with a linear trend. Possibly the deformation source of the subsidence and the uplift is the same, and then there is an interaction between the magmatic system of Askia and the rift. If we look at the modeling, one source is not enough to explain the observed deformation. Instead, with the interaction between the seal and the ring fault, we could improve the fit with the data. But however, there are further complexities like the presence of fluids or even the subsidence due to the rift opening that we could not model. As far as I know, there is a new project with a lot of seismic stations installed in Askia to study the microseismicity and check if the ring faults are active or not. And then last thing, during this winter, at some point, the lake that in general is completely covered by ice, the ice on the lake completely melted. between February and March. So it would be nice to have information about the lake project. With this, I can conclude. I don't know. Since I have time, I will show you another slide. We cannot really add the second ring fault inside for the lake because it's quite complex making an inversion with the Bayesian inference. There are too much parameters, but we did some tests with forward modeling, and as you can see here, the black line is the total displacement, and in this case, we could model the anomaly that we saw before nearby the lake. So, I mean, it was just an extra slide to try to convince you that the ring fault can produce part of the deformation. Thank you again.
Thank you, Adriano, for this interesting insight into Aspia. I'm sure there are questions. Let's see.
Do you have any feeling how much, what percentage of the deformation, what conventional model explained as the black micro deformation can be added to the report?
Looking at okay, all the experiments that we did, the test, I would say that for the 40 centimeter that we observed of uplift, only less than 10% is due to the ring faults. Less than.
We have another question up there.
I can do it.
Really need to know, just one question. So when you're modeling on the scale, you're using a uniform so
Yeah.
try distributed voltage, you can explain the state without the last time.
No, I didn't try the distributed opening. It was something planned, but in the end, we said, okay, actually, the thing is that we don't have any constraint for the ring faults and the depth of the seal, so it was only a test to understand which was the best parameter to choose for the seal and then make the forward modeling in the beginning. Then now we are implementing it on the other Bayesian software that is looking for the best model, so we are changing a bit the research line.
And you ever observe here or discontinuity in the information that would show the original factor of
I didn't get. For I mean, for us, the ring faults are buried, so are located. The top is 800 meters below the surface. If we tried with boundary element model to go too close to the surface, we got some strange anomalies. However, again, looking at the ground deformation obtained by the ring fault, if you move the ring fault too close, you have really steep deformation, and is not what we are seeing. So we try to keep them, let's say, at a certain depth, below 500 meters.
Sorry, but there was like another question up there, and if we accept this one, I think there one other. Sorry, just to be fair.
Just wondering, of course, when you add more models, more mapping to models,
This is again another things ongoing, and we are trying to understand which is the best way to compare, let's say, the different models. But yes, we are for the moment we have the variance reduction for this, and okay, is a good improvement because it's 10%, so is a huge difference. But yeah, I mean, the Annes is working on this part and the statistical part to make some tests. We have a lot of parameters, so I mean, we need to justify all these parameters, and it's quite tricky, the use of them.
Okay, and then one very last question in the front. No, please go ahead. Yeah, can you please?
So for we define the first layer and the second layer of the first the top of the ring fault and the bottom of the ring fault for the position and sides the A and B is an ellipse for the two coordinates, and then we can define the depth of the two layers and we create the mesh in between. So I don't know. Okay,
Okay.
I reply to your question.
Yeah,
Thank you for all the questions and the very nice presentation.
yeah, thank you. So we move on to the next speaker, Michel. That's going to tell us about a new project, ISVOLC.
Okay, hello everyone. So this presentation is essentially just going to give a quick overview of this new project called ISVOLC. And essentially the project is addressing the effects of deglaciation on variations in both seismic and volcanic activity in Iceland. Okay, so the project is funded by RANIS, the Icelandic Research Fund. Essentially it was awarded as a Grant of Excellence project in January this year. And it actually comprises essentially a collaboration of about 20 researchers, international researchers, both from Iceland and abroad. The institutes are shown on this slide, and these researchers are from 11 partner institutes. Okay, so the project officially started on the 1st of April this year. It has a duration of 3 years and a budget of about 153 million Icelandic krona. So that's equivalent now to about 1 million euros. The project itself will fund 2 PhD students working in Iceland based at University of Iceland, plus a postdoc for 2 years who will be based at the Icelandic Met Office, some contracting work and also field work in years 1 and 2 of the project, plus some software as well. So why are we doing this? Because glaciers cover approximately 10% of Iceland, and they have been retreating since 1890. And I mean, this is extremely evident when you look at these outlet glaciers in particular in Iceland. So here we have an example of Solheimajökull. This is an outlet glacier essentially on the southwestern side of Vatnajökull Glacier, which hosts Katla volcano. So here, this picture you're looking at is from 1997. Here we have 2000, 2003, 2005, 6, and 10. So it is very clear that the glaciers are retreating. The climate change predictions essentially in the future indicate that this is going to continue and at quite an alarming rate. So at the end of the last major deglaciation some 12,000 years ago, there was actually a 30 to 50-fold increase in eruptive activity in Iceland. This will happen again. It's no longer a question of if this will happen, it's a question essentially of when and by how much. Okay, so what is the hypothesis of the project? The main hypotheses are these, essentially that this melt loss is already affecting the volcanoes in Iceland. Essentially, it's generating more melt in the mantle due to decompression melting. It's also resulting in stress changes in both the mantle and the crust. And so these stress changes are affecting magma migration, and they're also affecting the stability of existing magma bodies. So in this case, they could actually either bring a magma body closer or further from failure. So if it's actually the former, this could mean more frequent eruptions in Iceland, and if it's the latter, it could mean much larger eruptions, both in terms of explosive and effusive activity. So it's also affecting earthquake potentially as well, or earthquake activity. So essentially by stressing major earthquake zones. So in the project, we're going to focus on both of these things. And by doing so, we're looking at 4 target volcanoes, and they're shown on the map here. Sorry, I don't think the pointer works. But essentially, so in the south, we have Katla volcano under Möttisjökull Glacier. Under Vatnajökull, which is the largest glacier you can see there, we've got Grímsvötn and to the north of that, Askja, which was just the topic of Adriano's presentation, a volcano that's currently in unrest. In addition to this, we're also focusing on 2 main seismic zones. So in the south, we've got the South Iceland seismic zone, and in the north, the Tjörnes fracture zone. Okay, so what do we actually plan to do in the project? Well, firstly, we plan to generate a new database of these ice changes, essentially since the end of the Little Ice Age, so for the last 130 years. On top of that, we're then going to create new 3D, or I should say 4D GIA models. So these are glacial isostatic adjustment models for all of Iceland. So essentially, due to the deglaciation, the crust is rebounding, and this term is referred to as glacial isostatic adjustment. Of course, this rebound effect is what's producing more melt in the mantle, and also affecting stress changes in the crust. So another work package, we're going to develop advanced 3D magma plumbing models, essentially of the target volcano. So of the volcano plumbing systems beneath these volcanoes. These will initially be based on the simple analytical models, but then of course we'll be building advanced finite element models after this with different degrees of complexity. So after this, we plan to generate future scenarios for the melt loss on Vatnajökull, so projections for the future. So this may be looking at 50, 100, 200, and 300 years from now, and then computing the GIA models based on this as well. Okay, so if we take a look at the actual work packages, there's 5 work packages in total involved in this project. So the first one, geodetic and glacier mass balance observations. So the first part of this is generating the extended time series of our GPS or GNSS observations across all of Iceland. So this involves essentially creating or updating the time series, I should say, for around 100 continuous stations, plus also our campaign observations as well. On top of that, we'll be re-estimating the countrywide, essentially, INSAR maps or velocities. So here we have an example from Druin and Sigmundsson on the right-hand side. Now, this is essentially the vertical measurements we're looking at here, or the near vertical measurements for all of Iceland, and this was estimated from Sentinel-1 data. So we'll be updating these maps, and again, this will primarily be using Sentinel for the INSAR analysis and decomposition, but on top of that, we'll be using other supersite data such as Cosmos SkyMed and TerraSAR X data, specifically in the regions of our target volcanoes. Okay, so, and of course, the other main part of this work package is generating these new time-variant ice history models for the last 130 years. So the next work package is primarily associated with the GIA modeling, the glacial isostatic adjustment modeling. For this, as I say, we'll create a new generation of 4D models. So the input of this, of course, will be the mass balance observations from work package 1, and also the geodetic observations. So essentially, the Earth models will be constrained using the geodetic data, yes, and essentially combining the Earth models and the ice history models produces our GIA model. The next main part of this work package, of course, is then re-estimating the changes in the melt production rate in the mantle. And this can be done by computing the pressure changes, essentially from the GIA. So work package 3 is the advanced models of target volcanoes. And as I say, initially we will base the work on known models from analytical models at these target volcanoes. Essentially, after that, we'll be producing new finite element models for each of these volcanic systems. And we plan to undertake this work in COMSOL. We'll also compute the Coulomb failure stress and see how this actually affects seismicity on main fault orientations in our seismic zones, as well as investigating how it's modifying local seismicity at our target volcanoes. So work package 4 is coupling of the GIA and the volcano deformation models. And what we plan to do in this work package is essentially project the stress field induced by the ice loss by the GIA onto our target volcano systems to see how this is perturbing essentially changes in the stress field around existing magma bodies. Is it bringing them closer or further from failure? How is it affecting magma migration pathways in the area, etc. We were actually initially looking at trying to physically combine or thinking about combining the two models, but of course there's a lot more added complexity there because of the significantly different both temporal and spatial scales of these two models, the GIA versus the volcano models. Okay, and work package 5, so this is hazard assessment and forecasting. So as I said earlier, what we really plan to do here is generate future projections of the melt loss for Vatnajökull Great Glacier. So at 50, 100, 200, 300 years into the future. And from this, essentially generate new 4D GIA models. So once we've generated those models, again, we can estimate the new melt production rates for these different time periods. Okay, so just quickly now, the dissemination plan for the project. I mean, we really want to make as much as possible publicly available and really as soon as this can be done. So one of I think the main advances here will be this database. We plan to create a publicly available database with all the GIA models and also the ice history models that we're using within the project. So this database will contain obviously all the GIA surface displacements and velocities. On top of that, any code that's generated within the project, so by the researchers or the students, will also be made available in some open source repositories such as OSF Home. Okay, so field work. So this year we're actually already undertaking 2 field campaigns. So one at Grimsvert, which was undertaken in the spring, and one at Askja as well, which was just done last month. So at Grimsvert, we visited, well, actually this was led by Heldur Geirsson at University of Iceland. And Heldur visited essentially 6 of our existing stations, GNSS stations there, and made measurements at 5 of these. So this comprised of essentially, in some cases, installing new equipment, so new antennas, solar panels, etc. And in other cases, just reoccupying stations that hadn't been visited for many years. On the lower left-hand side, here's an example of a campaign installation at HUSB, and this is situated to the southwest of the caldera. In the middle, again, an installation at SVV2, and this is right on the southern rim of the Grimsvert caldera. And then on the right-hand side, campaign GNSS measurements at Askja, and this is essentially at the station A404, which is on the 1961 lava field. So at ASCIA, on top of the campaign GNSS work, we also undertook leveling. This was led by Eric Sturkel, gravity and also gas measurements undertaken by myself and Melissa Pfeffer at IMO. So future ISVOLT meetings and presentations. So we're planning actually to hold a workshop just later this year at the end of October in Iceland. And this will mainly be to start training the PhD students and get everyone together working on the project. And Fabian Albino will be joining us, and Elisa Trasalti from INGV, and also Peter Schmidt from Uppsala. Freysten Sigmundsen will be giving a presentation with some new results at AGU in December this year. And then we'll have another project meeting at EGU in April the following year. So we've already hired 2 new PhD students to work on the project. One is going to start straight away, essentially. Well, she started yesterday, in fact, working on the volcano deformation models and, in fact, ASCIA, finite element modeling. We have a second student coming in October who will primarily be working on the ice history and the GIA modeling. And then we've got funding also for a third student through the University of Iceland Research Fund. So this student will be working on a combination of GIA and volcano models. We're also collaborating with James Hickey at Exeter, and he's just recently had a PhD project funded as well by the EPSRC. So this student will collaborate with us on the project and work on ISVOLT volcanoes. As I mentioned earlier, we do have funding for a postdoc position for 2 years, and I foresee that this postdoc would work primarily on work packages 4 and 5, so combining the GIA and the volcano deformation models, and then also working on the forecasting work package. So this postdoc will be based with myself at IMO at the Icelandic Met Office. If you know of anyone who could be interested, please drop me an email. And Peter Schmidt is currently working on updating the previous GIA model, and this hadn't been updated since 2013. So we hope to see some new results from Peter quite soon. Okay, thank you.
Thank you, Michel. Any question or comments about the ISVOLT project? Yeah.
Thank you, a great presentation. I was wondering how far back do you want to make your
We're aiming, apparently, for the last 130 years. So the glaciologists claim. But of course, it's, you know, the temporal resolution of these models is going to be, you know, greatly varied, right, depending on how far we go back in history and what kind of measurements that we have available. But yes, I mean, this is the plan, to go back at least 100 years.
How much bigger are the rock going to be during
The project has started. But no, okay, I'm just joking. I can, well, for example, so from Peter's last work on this, which was in 2013, at that time he estimated that there was 150% more melt being generated in the mantle. So, and obviously the deglaciation is continuing. Models will be updated, but I'm expecting it to be more, obviously, than that from the last estimate for the melt generation. Of course, then it depends on, you know, the timing it takes for this new melt that's generated to come from very deep levels, let's say greater than 100 kilometers, to the upper crust.
Okay,
There's a timing, yeah, and how much of that actually reaches.
You made it the right number. How much bigger would it be if you have
could you've removed all the ice. No, I can't give you an estimate, sorry, offhand, but of course this is what we're going to be working on, right? And this will be in the final work package 5, which is the forecasting and future scenarios. Yeah.
Anyone? Question? Comment? No? Okay, thank you. Michel, we're gonna move on. Thanks.
Okay, we move on with the last speaker of this first volcano session. The next speaker is Birhan Abera-Kebede from University of Pisa. And the presentation will be about the Tulumoye volcanic complex in the main Ethiopian rift.
So, hello everyone. As you can see, I'm not Biran. I'm Alessandro Rosa from the Earth Science Department of Pisa. And today I will present on behalf of Birhan Abera-Kebede, which is a PhD student working with us in our department. And this study that I will present will be an analysis of ground deformation processes on the Tulumoye volcanic complex in the main Ethiopian rift. So why this volcano? Tulumoye is located within the main Ethiopian rift, which is an active rift located in the northernmost part of the East African rift system along the axis, and together with as other volcanic system, for example, Corbetti or Aluto, this volcano is interested by intense heat flows and hydrothermal activity. That make this area a perfect site for geothermal energy exploitation and exploration. In fact, as you can see from this yellow star, there are already some power plants active in this area, and other active drilling are ongoing in the area for further exploration. A bit more in detail about the volcano-tectonic setting of this volcanic complex. So the volcano is characterized by a large caldera system with several concentric ring faults hosting various volcanoes, for example, Bora, Berecha, and Tulumoye volcano. And this area is also dissected by a cross-cutting system of faults. So we have the northeast striking faults pertaining to related to the active rifting in the area, the so-called Wonji fault belt, here highlighted in pink. And then we have other northwest and northwest striking faults, probably related to a previous phase of the rifting or to some inherited structures here highlighted in blue. So this volcano is actively deforming, but the nature of the deforming source is a bit debated. So we have two hypotheses about the deformation in the area. So it could be either magmatic or geothermal. So there are previous studies using INSAR on this area by Biggs et al. 2011 that used MVSAT time series from 2004 to 2010, and they observed a series of alternating uplift and subsidence phases in Tulumoye. They also modeled this deformation and infer a magma body at a 2.5 kilometer depth. And more recently, Albino and Biggs 2021 also analyzed Sentinel-1 data for this area along with other volcanoes on the East African rift system, and they observed continuous uplift starting from 2015 to 2020. So in this case, the deformation has not been modeled because it was more an overview, a large-scale overview of the old volcanoes, but this pattern has been interpreted with a magmatic, as caused by a magmatic source. So on the other side, for the geothermal team, we have Samrock that use magnetotelluric data to observe a big high conductivity body beneath Tulumoye, which has been interpreted as the plumbing system of the volcano, and another shallower high conductivity body here named C4, which has been interpreted as the shallow hydrothermal system. And Samrock used this observation to interpret the data from BICS and suggest that this alternating uplift and subsidence has been instead caused by this shallow degassing in this shallow hydrothermal system. So we try to take part to this debate, and we analyze Sentinel time series from Sentinel-1 Sentinel-1 time series. We produce average velocity maps, and we carried out the modeling and combine all this data, satellite data with the independent magnetotelluric data and seismic data for this area. So the main aim was to investigate the locus, magnitude, and scale of deformation, try to constrain the causes of this deformation, and try to build up an integrated model of both the magmatic and hydrothermal system based on this independent data. So for our time series analysis and velocity maps, we used the small baseline subset approach implemented in the ESA geothermal exploitation platform. And we produced average velocity maps for, from both ascending and descending tracks for the time period between 2014 and 2017, which is the longest time period allowed by the ascending track. There are no more acquisition after 2017 for this track. But then we also processed time series between 2014 and 2022 from the descending, and again, as I said, we have just the shortest time period for the ascending. So here you see the two networks for the descending on the top and ascending interference and ascending tracks. So here you see the result, the average velocity maps for the short time period that we obtained for Tulumoye, and here for negative values indicate range decrease. So both maps are show this pattern of range decrease with values of, I don't know if it's clear, but values of more or less 40 millimeters per year in both tracks. And so this is consistent with a vertical uplift pattern. The pattern is also located within the caldera between Bora, Berice, and Tulumoye. And it is more or less 10 by 10 kilometers wide. And it's elongated more or less in the northwest of this direction. We also took a look to the time series, and the descending track, which is the long one, shows a rapid uplift phase starting from 2015 until 2017 with 40 millimeters per year, more or less consistent with what has been observed by Albino and Biggs. And followed by a period where uplift continued but slowed down to more or less 12 millimeters per year until 2022. The ascending track was very noisy, but here we put it as a comparison, but more or less looks like showing a similar trend, at least for the short time period. We also compared this time series with microseismicity recorded by Greenfield et al. 2016, and you can see that here is the seismicity is represented by this purple curve, and at least for the time period 2016-2017, this rapid uplift phase is also accompanied by increase in the microseismicity activity. So we model the deformation associated with observed by the average velocity maps for the shortest time period, and we use a pretty standard approach. We first subsample the two average velocity maps using a quadripartitioning algorithm, and then we create a covariance metric of a spatially correlated random noise, and we use by sampling an area in the top right corner of the map. And we use this information to carry out a weighted joint inversion of the two maps, assuming an ocadal tensor dislocation source. So trying to model it as a seal. For the inversion, we use a Monte Carlo simulated annealing algorithm followed by a derivative approach. Following the approach of Cervelli et al. 2001. So here you can see the result of our modeling. So in the two left panel, there is still the observation, the model is in the middle, and the residual on the right two panels for ascending and descending. So our best fit model is represented by a northwest southeast striking seal, which is located at a depth of 7.7 kilometers and opening at a rate of 0.85 meters per year. I forgot to say that we use an elastical space. So assuming an elastical space, this will correspond to a volume rate change of 8.9 times 10 to the power of 6 meters cubic meter per year. Yes, the model explained quite well the residual, and here on this table you can see further parameters for our seal. So the seal is quite elongated in the northwest direction with a length of 8.7 kilometers and the width of 1.2, and is gently dipping to the southwest with 11 degrees. So we use the VCM of the spatially correlated noise to create 100 simulations of the noise that we had to our observation to calculate the uncertainties. So here you see the result of the calculation, and you see that the parameters show very narrow variability, and our best fit model falls quite well within the maximum of the frequency distribution for this parameter, which suggests that our parameters are quite well constrained. So yes, we combine our model with this other independent geophysical observation with magnetotelluric and seismic data, and as you can see, the comparison with the magnetotelluric suggests that the seal, it's located on the upper edge of this high conductivity magma body, and also as this southwest dipping, which is similar, it's not very clear from this view, but it's similar to the southwest dip that has this big plumbing system. So also, this seal is located 1 or 2 kilometers below the cluster of microseismicity observed during 2016, 2017, and it's subparallel to the northwest striking fault system of the caldera, which could suggest there is a structural control for the emplacement of the seal. So try to collect all this information in one conclusion. So it could be that these northwest-oriented faults could act as a channel, could help in channelizing the magma into this elongated seal, and also favor the fluid migration toward the surface. And this is also suggested by the microseismicity and the surface manifestation in correspondence at surface above this emplaced seal. So this could suggest that this seal could represent an important heat source in the western part of the geothermal system. So and try to combine our observation with the previous inter-observations. This alternating uplift and subsidence could be explained with the inflation of the magmatic system that generate uplift, and at the same time with the gassing of the hydrothermal system that can generate the subsidence. And this has been something already observed for other volcanoes in the main Ethiopian rift, for example, Alutu. So this I conclude. Thank you.
Thank you.
Thank you very much. We have time for some questions. Yeah, Julia, there's one up there. Can you have the microphone, please? Yes. Okay.
Oh yeah.
So my question was, the volume line, certain volume line of the end.
Yeah.
I wanted to understand whether that was really a different model, or if it's taken
Okay, so the question is if the different source that we model here with this data is different from MVSAT because of the source or because the temporal, the time that the different time period that we investigated, right? So you use a penny-shaped crack for your model, right? So basically assuming modeling it as a seal. So I don't think there could be too much difference in terms of the surface response of this seal. I would probably more, I would probably be for the other option. I mean, it's because of the time period investigated. Looking at the magnetotelluric surveys, we can see that there are also more shallower sources between 0 and 5 kilometers. So it could be that what you observed in the previous phase could be something related to more shallower sources. So I will not be surprised. So. Not actually. Yeah.
Okay, yes, please.
Yeah, sorry. I didn't understand fully the differentiation between the hydrothermal or calling geothermal source. You're meaning probably hydrothermal source from just pressure, right?
Yeah.
Can you repeat the question?
Oh, yes. He is asking for clarifying better the surface deformation and what's caused the surface deformation and what caused the deeper deformation, right?
Yes. So the only way to distinguish between them is using gravity, right? Do you have a way of
Well, for the you could be able to model a surface deformation related to geothermal activity. In this case, there are no evidences of a shallow source. But if the shallow source will be the cause of deformation, it could be able to be highlighted by the modeling. I mean, the modeling could solve this. Regarding the relationship between the surface deformation and deeper one, well, it could be that the two sources have a different temporal evolution. So maybe at surface you can see alternating uplifted subsidence related to the gassing and recharge of the shallow system, while deeper sources can be related to other deformations, so behave in a different manner. In our case, we just observed this continuous uplift that progressively decay, and there were no evidences of other clear evidences, at least, of shallower activity that could sum to this deeper source. I don't know if I responded. Thanks.
Are there any other questions?
I have one.
Okay, please.
So basically, because the context is we have high flow of temperature and thermal systems, so flux of fluids, and especially now that the time series show really nicely this exponential decay on the deformation, I was wondering, what do you think about maybe some viscoelastic relaxation and how it could impact the model if you consider some viscoelasticity?
Okay, regarding the viscoelastic modeling, it has been shown in recent studies that when you try to, we modeled the short-term deformation, so between 2014 and 2017. So according to recent models, you can assume that in this very short time, this sudden pulse, let's call it pulse of magma, can be assumed as elastic. So we didn't explore viscoelastic solution because we are not analyzing a longer time period to investigate, to be able to distinguish the viscous response on the long term. So it could be something to explore with longer time period.
One.
Yeah.
Okay. Okay, good. Thank you.
Thanks.
And there was another question up here.
Oh.
Hi.
Hi.
I just want to ask, what happens there?
Okay. In the jet portal apply two main atmospheric correction, which is the IPS with a median filter on the temporal space, and then a correction on the layered component of the atmosphere using the linear correlation with the topography, so using the DM. Yeah. Thanks.
Yeah, maybe follow up on that is, you said the 8 million descender. I can't remember which track it was, but one of them was really noisy in comparison.
Yeah.
Be cautious about kind of interpreting that as kind of an uplift pattern. There's so much noise in there.
Yeah, we didn't find any other way to remove more the solution. Actually, using the jet portal, you don't have too much control of lot parameters. This is something that I would really like they improve. But yes, with for what we could do, there was no way to remove that noise. This is something else which is out of our control. You cannot look at the single interferogram, or, I mean, you can look at the single interferogram, but then you don't have any way to exclude them from the processing. I mean, they are excluded on the basis of like variance of poor coverage. Yeah. Yeah. Yeah, it could be. But we didn't look carefully into it yet. But thanks for the one.
Thank you. We can take one or two questions.
Also, if you have questions to any of the other speakers, we can still ask them because we have some time left.
So remember that there will be a round table after all the 3 sessions from the volcanoes when we have to kind of have some seats question and report it to ESA. So if you have in mind and if you really consider to come to this round table. So here, if there is no question, I think we can close this volcano 1. So please come to the next one, the second and the third volcano session in the afternoon. And I remind you that there is also the poster session. So there will be, of course, tomorrow afternoon, and there is many volcano poster regarding INSA application. So thank you again, the speakers.
DING and MOFC. So DING is here and MOFC there. Okay, so after the unrest started, we installed 3 new continuous stations in the area. So 2 within the main Askja caldera. This is Yonk and Kask that you can see on the map. And then Tank, which is on the most northern rim of the caldera and essentially transmits the data. Okay, so historic eruptive activity at Askja volcano comprises both large, essentially explosive rhyolitic eruptions, and also basaltic effusive eruptions. So the last eruption to occur here was in 1961. And essentially this was a small basaltic fissure eruption. So the fissure actually opened up here, it was 800 meters long. And this produced a lava field with a volume of about 0.1 cubic kilometers. So just to give you a reference, this is a bit smaller, essentially, than the volume that was extruded during the first Fagradalsfjord eruption in 2021. So the most recent caldera, or explosive eruption to occur in Askja was in 1875, and this was actually part of a major rifting event between 1874 to 76. So the caldera that actually formed is Lake Eskjavart, so that's the one in the center here. And it also formed a small explosive crater called Lake Beatty, and that was actually shown on the first slide. All right, so prior to the onset of this inflation, long-term subsidence was occurring at Askja. If we take a quick look at the next slide, this is the long-term leveling data acquired by Eric Sterkel. And this slide is essentially showing the data since 1968 to before the inflation started in the summer of 2021. So we can see here this initial subsidence was actually occurring from 1968 to 1970. Following that, we have this quite sharp change to inflation. We then have a gap in the measurements, unfortunately, and this is because of the Krapler fires during this time. And then when the measurements resumed again in 1983, you can see that we have continued subsidence occurring at the volcano, but at a far reduced rate. So the suggested processes behind this long-term subsidence have essentially included cooling and contraction of an existing magma body, plus magma outflow potentially, and also viscoelastic effects. So the GNSS observations at OLAC suggest that this change to inflation actually occurred at the end of July 2021. And the inflation, of course, is also observed on INSAR. You saw this from Adriano's presentation earlier, and also on the leveling profiles that have continued. Okay, so here we're just looking at the previous subsidence that was occurring. So as I said, the leveling measurements show this from 1983 onwards. Here we're just looking at sentinel interferograms on the top panel from 3 different tracks. So here we have 2 descending and 1 ascending. So here we see the subsidence signal in blue amplitudes here. And on the bottom panel, we've got the near east, essentially the decomposition results, the near east and the near upper vertical displacements. So they show that essentially the maximum center of the deflation was situated to the north of the Eskjavart caldera. Okay, so here again, now we're just looking at a series of interferograms, but this is from the inflation period onwards, so from July 2021. So on the left-hand side here, we've got both the wrapped and unwrapped interferograms. Now these are spanning from end of July 21 to September 2021. On the middle section here, we've got one of our campaign GPS time series, and this is from the mid-Askja station, and essentially this is situated in the main Askja caldera. And on the right-hand side, we've got the time series from OLAC, which is the continuous GPS station. Okay, so here we clearly see the subsidence that was continuing, and then a sharp change to uplift on the campaign site, and the same for OLAC. Okay, the subsidence here, and you can see the magnitude of the inflation compared to the subsidence that was occurring previously. All right, so if we look at the time series from both the GPS data and the INSAR, it seems that actually the source of this inflation was not static during an extended time period. So what we see looking at the INSAR, so here we've got essentially the decomposition results from July to September 21 on the top, and on the bottom from September 21 to September 22. And you can see that there's a shift in the main location of the inflation signal that's observed. So essentially, originally, the signal was centered around our GPS station, OLAC, and after that time, the signal rotated actually in a clockwise direction further to the north. If we look at the GPS time series now, we can see at the start or the onset of the inflation, the initial rate was significantly higher. After September 21, the rate is actually reduced, and then since this time, the rate has been stable and the source location has been stable for this inflation. So what I would suggest is actually the data could be modeled using two separate sources in these two different time periods. So also if we have a look at the decomposition results shown here, so on the left-hand panel, we've got again July to September 21, and on the right or the middle panel, September 21 to September 22. And now if we look at some transects through these decomposition results, we can see that in time period 1, here we look at the near-up displacements, and this is, in the blue-purple colors for the first time period, T1. Here we can see the nice inflation signal over the caldera. So this is the west-east transect going through here. But we can see actually on the eastern side, it's showing subsidence. We don't see the same signal in the latter period. So what we've actually done, as I said, modeled this as two separate time periods and using different sources. So in T1, we actually have two sources required to model the deformation that's observed. So we have an inflating sill type source, which is shown by essentially the black polygon shown here. And then we also require a deflating source to match the subsidence signal that was observed on the decomposition result. And that's shown here by this magenta sill type source. So both are near horizontal sill type sources. However, the upper one, located at a depth of just below 3 kilometers, is inflating, and a lower one, located at a depth of about 4 kilometers, is deflating. Okay, for the second time period, this can be modeled very well just using a single source. So for time period 2, where, as I said, the signal is broader here, and the source seems to have migrated to the north. This can be modeled using a single Akada dislocation, again at a depth of about 3 kilometers. And the volume change associated with this is about 11 million cubic meters. So if we take a look at the seismicity as well, since the onset of the unrest, this is also quite interesting. We don't see a significant increase in seismicity that we see associated with unrest periods at our other volcanoes in Iceland. For example, associated with dike intrusions, but also sill intrusions. So here we're looking at seismicity for earthquakes greater than magnitude 0.5, as this is the magnitude of completeness here. And on the left-hand side, you can see the map, and with the blue box is essentially the region that I've extracted the earthquake information from. So if we look at the panel, okay, so this is earthquake activity since 2016, and I've chosen that date because this is after the Bardabunga eruption. Okay, so here we see a slight increase in the start of the unrest, but essentially after that time, it just reverts to background levels. However, if we break up the seismicity and look at different areas, then we do see more subtle changes. So here we're just looking at the seismicity, again for the same time period since 2016, but for the area which includes Eskivart, which is the lake here, and the western side of the main Askja caldera. And in this case, again, we see an increase in the seismicity at the start of the unrest, end of July 21. It then flattens off briefly, but then starts to increase again. If we look at seismicity just in the known geothermal area, now this seismicity here has been occurring for decades, so it's not something new. If we actually look at this, it's very difficult to see any change whatsoever in the slope related to this unrest. Okay, so what is the cause of this inflation? Well, for T1, I mean, the modeling is suggesting that this is upward migration of magma, essentially just within the upper part of the volcanic plumbing system beneath Askja. So here we have a movement from about, let's say, 4 to 3 kilometers depth. So a deflating source at about 4 kilometers with magma rising to a slightly shallower level. However, for the second phase of inflation, we don't see any evidence for this shallow subsidence source. So here, this may be triggered by an influx of new melt from much deeper within the plumbing system, so possibly greater than, let's say, 16 kilometers depth. The total estimated inflation volume for the unrest to date, so using these shallow sources, is about 25 million cubic meters. So I do want to say, of course, this is just one of many models to come. You saw an alternate model presented earlier today by Adriano, essentially with an inflating sill and movement on the ring fault system. What I've shown you here is essentially a series of models. Well, two sources, or so I should say two sources in T1 and a single source in T2. And this, of course, assumes a uniform elastic half space. So initial finite element, more complex models have already been run by one of the students based at University of Iceland, and her model incorporates topography and heterogeneities. And this actually suggests that the depth of the inflating source could be up to a kilometer deeper than I've shown you here. So I just want to say I think it's very important to run these different types of models. I've shown you a simple analytical model which I believe can reproduce the deformation observed, and it also corresponds with other data sets. So the gravity, the seismicity, the geochemistry, etc. But it's very important to run more models at Askja, and many more will be run in the future with added complexities. And these models hopefully give us a better understanding of the subsurface plumbing system and also the uncertainties involved in the individual models. Okay, thank you. I forgot the last slide, but if you have questions about future scenarios, then please just ask. Yes?
Oh, you need to wait for the microphone.
You mentioned gravity. Are there some gravity data available?
There are, and in fact, a paper has just recently been published by Matthias. Is Andy here? No. Yep. Andy, what was the journal this was published in? No, sorry, neither can I. So yes. So the initial gravity results essentially indicated no mass increase beneath Askja. So this was for the initial period of the unrest. I mean, of course, there are some uncertainties, in the data and this study. But I mean, in reference to this would support the model that we present here, for essentially initially in phase 1 or T1 of existing magma just migrating up to a shallower level within the system. I guess we'll see what the next gravity results show from this summer.
Catalina was right. Well, why don't you give it to Catalina? She's right behind you.
Hi, I have a question about the model because, well, this model with the too narrow sill, it sounds a bit like weird animals, right, in terms of magmatic source. And, well, I saw it's mainly based on the fact that in the vertical, you see this signal that needed to be explained. So my question is that could it be the fact that because the deformation was much sharper at the beginning, that assuming that there is no north component gets mapped in the vertical, and maybe a solution could be if you have the GPS, you could just remove from the north component projected onto, and then solve this, because it seemed like the information is a lot. So even the north component, sometimes, it's a small percentage, but of a big number. And because I noticed that the first time period is.
If you
thought.
No, so yes, certainly it could be related to noise in the input interferogram. So for this model, actually for both time periods, we include 4 sentinel interferograms, 2 ascending, 2 descending. Also data from the continuous stations, but of course in T1, this is less data because we don't have the data from the 3 additional installations that were done after the onset of the arrest. Plus, it includes data from 4 campaign GPS stations. But, so yes, part of it may be related to noise, but also if you look at the probability distribution functions for that inversion, the width of the sills is not well constrained. So for the second period, it's really quite well constrained. And the depth is for both, but the width for T1, so yes, there's quite a big range, right? So they could be significantly wider than from the optimal model that I was showing you on the screen.
Thanks.
Paul, do you still wait for the mic?
Is the lake doing anything? Changes in lake level or getting hot or cold or?
Yeah, so we just did a campaign in August, end of August, and essentially we went to VT. Let me bring it back up. Okay, so this is VT Lake in the foreground here, and in the background is the Erskivat caldera. So this caldera formed after the explosive eruption in 1875. This is an explosive crater, which also formed during that eruption. So we routinely do gas measurements on both. So at VT and also on the southwestern edge of Erskivat. So to answer your question, so far there has been no change in concentrations of the gas measurements, no change in the ratios of the gases, no change in the temperature of the fumaroles that have been measured. However, there has been a slight increase in the temperature of the water in both VT and in Erskivat. However, I say that it's very clear from this year that the lake level is significantly lower on both. So in Erskivat, it may be due to the inflation. So in fact, more fumaroles are now exposed that were under the water previously. And in BT, we think essentially this is just due to the fact that last winter was nowhere near as harsh as the previous one, so there was much less snowfall, and I think there's less groundwater infiltrating the lakes, infiltrating BT. So this alone could explain a slight increase in the water temperatures that we're observing. It is not really significant. We're talking a few degrees increase.
There's no CO2 bubbling out.
Well, yes, we measure CO2 in the fumaroles and H2S, but we haven't seen any change in the concentrations or, the ratios of the gases.
Yeah, that was a really interesting talk, Michelle, and I'm wondering if this low seismicity or this really non-remarkable seismicity that you show is normal for the volcanoes in your part of the world, or what did you expect, in other words?
No, usually I would say no, and we expect to see a significant increase in seismicity when we have a new intrusion. Yeah. So the question is now, is the lack of seismicity because the volcano was subsiding first for nearly 50 years, So, of course, the stress in the upper crust has been perturbed as a result of this, and maybe it's just going to take much longer for the stresses to build up to that level where we start triggering, the seismicity, the fracturing that would be expected. To be honest, I don't really have an answer for it, but it's intriguing.
Okay, we should move to the next talk, which is Falk Amelang. and he'll be talking on what's next for Mauna Loa volcano, stress changes due to the 2022 intrusion and eruption.
Yeah. Okay. Okay, so I'm going to talk about, it's Paul just said about Mauna Loa. It had a big eruption last year, finally. The topics I'm going to talk about are, giving an overview, about 20 years of deformation data. Then we did a successful prediction of the location of the eruption. And I'm going to talk about a very interesting earthquake at the summit prior to the eruption. Okay, we have, Mauna Loa, the big island of Hawaii. The two volcanoes are Kilauea and Mauna Loa. They are characterized by rift zones. Mauna Loa has a rift zone which goes through the it has a rift zone which goes through the entire volcano. Eruptions typically they start at the summit and then they go in. A dike propagates into one of the rift zones, and previous eruptions at Mauna Loa happened in 1950, 75, and 84. So it was 38 years since the last eruption. But in some time periods, it's extremely active. In the end of the 19th century, it had an eruption every couple of years. For the structure of the volcano, something which is important is the big décollement at the base of the volcano. Mauna Loa, by the way, is the largest volcano, the largest mountain on Earth, about 9 kilometers from the ocean bottom to the top. And because of the growth, magma intruding into the rift zone, there's occasionally earthquakes on the décollement fault at the base of the volcano. What really matters is whether an eruption occurs from the northeast or from the southwest rift zone. If it happens from the northeast, the slopes are not very steep, but in the southwest, they are extremely steep, and so the flows can be very fast. Here's a giant flow from the 1950 eruption, and in this eruption, it took only 3 hours from the moment the eruption started until the coast was reached. And since then, there has been lots of coastal development, beautiful hotels like this one, and there's, of course, concern whether for eruption from that, whether there will be enough time to evacuate people. Just a beautiful picture of the eruption from 22. Luckily, it went to the northwest rift zone, so it didn't pose any danger, any hazards to people living there. It was just a beautiful eruption going on for 2 weeks or something like that. And so something what also happens at Mauna Loa, I mentioned the décollement, the pretty frequent décollement earthquakes. Generally, when you have rift zone eruptions in the 1 or 2 years before an eruption or after an eruption, there is a décollement earthquake. So what is happening is you're putting the volcano, the flanks are moving apart, and that creates space for magma to intrude into the rift zone. And once magma has intruded, then it pushes on the décollement fault, and that's what leads to the décollement earthquakes. Since 2002, we have continuous GPS measurements. There was a period of intrusion back in 2004, 2010, and then on the left side, on the west flank, you see that nothing happened for a couple of years, and in 2014, it started to inflate again, and that then continued until the eruption happened. And you see a significant difference between the west flank and the east flank. Actually, there's a factor of 2 different in the y-axis, and in the east flank on the right, it never stopped flank deformation. On the western flank, it did stop. So during this, we have excellent INSA data of this intrusion period, largely starting with the Cosmos SkyMed INSA data from the Hawaii supersite. The INSA essentially all the time shows almost the same signal, and there's secular seismicity happening once in a while, some swarms. The INSA data or the geodetic data can be best explained with a little weird magma model. So it's a dike-like magma body, just sort of lined with the rift zone, rather in the south of the caldera. But it's not the dike-like magma body is not the only thing. Then you also need the inflation source to the east of the rift zone. So it's a dual body magma reservoir, and that explains in particular the asymmetry in the vertical deformation. It shows vertical deformation. So inflation during these different time periods was almost the same, but in 2015, 2018, for this time period, you can see that the inflation pattern shifted to the south. Somehow this magma body moved, and after that it moved back further back to the north. What could be essentially it's exactly the same pattern since 2018. What was observed during 2014-15 and in the previous inflation period. So what could be the explanation for that? One possibility. So that there is explanation for the magma body to move southward. One explanation could be stress changes from the Coleman slip, but they are associated with a symmetric stress change. So there's not really a reason for the magma body to move southward. The stress change due to the magma source, it's again symmetrically uniform around the dike. But the topographic stress field is different. The topographic stress field decreases, topography decreases to the south. That creates a topographic stress gradient stronger in the south than in the north. And we think that is the reason why the magma body migrated southward. And so it's a summary of what happened up to 2020. During 2000, the magma body moved to the south, and if you look at the stress field after this, the stress field is most extensionally north of the magma body, and then of course the magma, the dike could also propagate upwards. So then we had the 2022 eruption, and sure enough, the eruption happened from the northeast rift zone, which of course was good because no hazards, and so the stress changes, with the stress changes, we have essentially predicted the location, not quite the precise location, but the general location of the dike, which sort of shows that the stress change models work well. But I have to admit, the random chance was pretty good because there's only 2 possibilities where the magma could have gone. Okay, now I'm going to talk about the 2002 eruption. The volcano continued to inflate, and then a couple of months, 2 months prior to the eruption, inflation became pretty rapid, a factor of 2 faster than before. This shows the that was before the eruption. And after the eruption, it shows the horizontal displacement. So there was rapid or rapid deformation immediately after the eruption. I'm not going to talk about the eruption itself very much because there was so much deformation. It's difficult to interpret what has to be done, of course. But so after the eruption, there was this a significant decay of the reinflation rate, as we have observed at other volcanoes, of course, as well. So what do the GPS vectors show? So this is a period prior to the acceleration of deformation. It shows the typical pattern. If you go a little bit for the last 2 months prior to the eruption, there's a difference. The vectors are much larger close to the caldera, which indicates there was somehow a very shallow source active or more magma going into shallow levels than previously. During the eruption, okay, that's the deformation due to the dike. There was about more than a meter of deformation, and then later on during the eruption, we see deflation from the reservoir evacuation, and after the eruption ended, it ended on December 12th. We see reinflation in the north and still continuing deflation in the south. So that indicates some magma migration within the reservoir. In the early pre-eruptive period, the vectors are rapid reinflation, long vectors, very close to the caldera. So again, magma going up, inflating at very shallow levels, and a little bit later, there is relatively less inflation directly at the summit. So indicating intrusion, magma intrusion at deeper levels. Yeah, and okay, so just again, this typical inflating pattern over all the time period, that is what it shows here. And now it is getting closer to that what we had previously. Still a little bit more inflation close to the summit, but it's decaying. So the shadow source is is more active at the moment. And that, of course, is also seen in the insert. This is a vertical. I haven't done very much of that yet. The vertical and the horizontal clearly shows that in the post-eruptive period, deformation is much more concentrated, again, indicating the shallow reinflation source. Okay, if you look at the longer-term picture, this shows the horizontal GPS on both flanks again. It was a big eruption, but in the overall picture of the volcano, it's just a blip, not very significant. Something which is striking, as I said before, is that in the eastern flank, there was deformation all the time on the flanks. On the western flank, not. So what could be the reason for that? And Mauna Loa is, it's very big, 4 kilometers high, more than 4 kilometers. So you get significant orographic rainfall. And there's easterly trade winds all the time. So we would expect more precipitation, or there's more precipitation on the eastern flank than in the lower flank. So one possibility could be would be nice to figure out that the precipitation, infiltrated rainwater, plays a role for the continuous eastern flank deformation. Prior to the eruption in March 2021, there was a magnitude 3.6 earthquake at the summit. You can nicely see the fringes. It ruptured. The surface. It ruptured the caldera floor. Something what we sort of would expect. You inflate the volcano, and then you start to get earthquakes. There was the insert time series shows that there was in the half 2 months prior to this earthquake, there was significant increase in inflation. So it turns out so this earthquake was on March 6th. Couple of days, a day later, 2 days later, there was floods on Hawaii. Actually, unfortunately, not on the island. Well, fortunately, okay, I don't want to get into that. For my science, unfortunately, not on the big island. It was on the island of Maui, 160 kilometers from the distance from Mauna Loa. Okay, there was something similar precipitation at Mauna Loa. It could have maybe contributed to this shallow earthquakes, to this shallow earthquake. And we had a paper published a couple of years ago, the 2018 eruption of Kilauea. It was preceded by very significant, the most significant precipitation over quite a long time. So we are saying that yeah, maybe the water contributed to it, though it's controversial. But there's not much. You can't really say much about the rainfall later. It was just much more wet. And so it turns out so this is now a time series of precipitation derived from the Global Precipitation Measurement Mission for Mauna Loa. There was significant precipitation as well. It just shows the last or total period of 14 months, but in the last 2 months prior to the eruption, about 40% of the precipitation happened. So it was a factor of 4 or 5 more precipitation than normal. So it could have contributed to this earthquake. It was very shallow. The rainwater infiltrates and maybe moved. It had to move forward. Okay, that's all what I have. Thank you for your attention.
Okay, we have time for a quick question.
Thank you for the presentation. So maybe I didn't quite follow. So you said that maybe there is a triggering of the 2018 eruption due to precipitation, but you also used the precipitation factor to perhaps explain the asymmetry of flank motion across the rift. Is it right? Could you elaborate, please?
Yes. So the 2018 eruption that was a Kilauea. It was a different volcano. Yes. And so what I think, so the eastern flank of Mauna Loa, it's moving all the time, slowly, and that is a flank which receives more precipitation. So maybe the precipitation is the reason for that. And then we had this earthquake in 2021, which happened after significant precipitation. So precipitation could matter quite a lot to modulate this volcano. Of course, it's difficult to prove. But basaltic rock, it's very easy well, it has lots of cracks, so water can go pretty deep and then accumulate. And if it accumulates at a fault or something, then you have higher water pressure, pore pressure. And we know that pore pressure is what can trigger earthquakes also.
So in other way, in order to explain the asymmetry with precipitation, you need to have a fault, lubrication somehow. So you need to incorporate a fault in your model. Yeah.
Yes. Okay. So I didn't talk about it. We used to have the fault in the geodetic models at the base of the décollement, but there's actually no constraints from the geodetic data. You can put it anywhere, and the data just don't have this resolution. So there is to explain the geodetic data, you need a fault somewhere, and we have it. Yeah.
Okay, thank you very much, Volk. The next speaker is Patty Mothers, talking about variable ground deformation at Chile's
volcano on the Ecuador-Colombia border.
Thanks. I'm going to move this closer. No?
You're okay.
Okay. So how do things work? Is this, but which is,
Pointer
how
to
do you
work.
point it?
The pointer's not working.
Oh, it's not working.
Well, it worked for Michelle, but
Oh, okay.
pointer.
Try this one.
Yeah. There you go.
It was. Okay. Good afternoon, everybody. It's a pleasure to be here. And this is my first Fringe meeting, by the way, so it's great after a long time of not going to meetings. So the work I'm doing is a work in progress, and it deals with the variable ground deformation rates that we've observed. Actually, we've observed them since 2014, but especially now in May 2022 at a volcano on the Ecuadorian-Colombian border. And I'd like to give credit to my co-authors, some of the Instituto Geofísico, Pedro Espín, who's here doing his doctorate, and Mauricio Battaglia, and also colleagues from the Colombian Geological Survey, and also give credit to supersites because Ecuador is a supersite. So what is the motivation that I want to talk to you about? So we have really strong ground deformation. It's been seen up to not on the average of recently, especially since 2022, of about 9 centimeters a year at these two, especially one volcano without an eruption in about 15,000 years. And what patterns do we see between the ground deformation and the seismicity? There's 2 activity nests. And by combining, eventually combining, because as I said, this is a work in progress, the INSAR and GPS time series, I'd like to be able to derive and improve propagation models and also where do we think we're going. While the volcanoes are analogs for this case, the one I come up with is Campi Felibre, possibly, and producing at times this situation of over 5,000 earthquakes a day. And that is 600,000 earthquakes since 2014. So will this volcanic system erupt? That's the big question. And when you're sitting there watching all the earthquakes come in at my observatory, you know, now we have a little bit better understanding of it. But if Susie was there back in 2014, and I think Juliet also, it's a very disturbing thing. And we're not talking about little quakes necessarily, but a lot of them are felt earthquakes. So the areas up along the Colombian Ecuadorian border, we have the Pacific Ocean here, and this little square encompasses a zone. And it's cut by faults, some which are related to the movement of the North Andean sliver, moving up to the northeast because of the collision of the Carnegie Ridge and the Nazca Plate. But anyway, this is the volcanic area here, and we've had 2 earthquakes since 2014 that are 5.6 magnitude. This one here with the star, and this one here last year in July. And then there's another one that was felt here in a community of 4.3, and another one here in 1868, a 6.7. A study was done with receiver functions and using our seismic network, which is not, especially when they use the data, was not very dense at that time. And it shows slow velocity zones, and this is starting in the north and going southward. And it shows that there's a possibly slow velocity zone suggest a mush accumulations around the Chiles volcano area. So I'm not surprised about that, but I'm surprised that their receiver function study didn't show any others where we have oodles of other volcanoes. But nonetheless, that's what this study by Koch showed, and I think it was a very nicely done study. And it kind of gave me incentive to use this in this talk here. So this volcano is old. There's a date on it of about 460,000 years at the base of it, and it has a summit of 4,600 meters. It had effusive lavas apparently in its last eruptive activity. There's been one study done on the volcano, and the last eruption was possibly produced lava flows 20,000 years ago. There's another little volcano over here that's related to, it's not a parasite, we don't think, but it erupted about 3,500 years ago with dacite andesites. But that doesn't seem to have any relationship to this bigger volcano because there's very little seismicity there. The GPS, as I'll show you on some of the vectors, there's just nothing happening there as far as we can tell. So This is another plain view map of the zone, this volcano with its caldera open to the north. And the area that's the hotspot of activity is to the south of the volcano. And then another area that we never even paid attention to. I mean, Ecuador is not a very big country. It's about the size of Colorado here in the States. And this is an area here that looked like it was possibly just glaciated, which is true. It's all the average elevations here between 3,600 and 4,200 meters. And this area never really appeared to have anything. But here was a larger caldera that's probably extinct called Chalpatán. And that, okay, we knew about it because it put out some big ash flows years ago, well, 200 and some thousand years ago. Here's a view of one of the new GPS stations we put in, and this is the wall of the caldera to the south where all these glacial, alluvial glacial deposits sit. But probably within that whole package, which we can't see yet, is a package of volcanic deposits, because just off of here, there's some strata that's really interesting and I barely looked at, but nonetheless, it says that things happen here. And so now I'll show you. Susie Ebemer worked here back in 2014, and then starting on the 1st of October, and there was an abrupt onset earthquake swarm of over 5,000 events a day. And the GPS displacements about 1 centimeter horizontal and 1.5 centimeters vertical preceded a 5.6. The earthquake 5.6 was in this area here. And afterwards, the system went quiet for 2.5 years. So these are some of the located seismic events at that time, okay? And we only had 2 GPS stations on the volcano. One was there, and the other was off of the picture here. So we weren't very well equipped at that time. We had 2 seismic stations as well. And what you can see, this is some of the RadarSat and Cosmos Skymed, basically the modeling of of those events. And here you can see with this particular station here at Chiles, right here, that there was a gradual northward, eastward, and up movement right before the earthquake, and then everything basically quieted down after that. And this is the bars of the earthquake. So it's 5,000 events a day are here. Here are the swarms. This is occurring in 2014. Then, as I say, we went quiet for 2.5 years. God bless to have that quiet time. And then you have activity picking up again in 2018. And then 2021 a little bit. And then 2022, bang. It starts on the 27th of May, and then it went on for a couple of months. That is with almost 4,000 events a day. And in that period, we had 110,000 earthquakes that were recorded, all of them about more than a half, about 0.5 magnitude. We have 8 large earthquake families. We have locations in the 2 nests. And this is a swarm of 2023. That is, it hasn't yet pretty much finished. When I say finished, you get accustomed to having 400 to 500 quakes a day, and some of them which are magnitude 2, some even magnitude 4. So these are important things. And we have a flip-flopping here of where these events are happening. So first of all, they occur up near the Chiles, right at the base of that big volcano. And then on the second time around in this period of 2017 to 2020, they're occurring at the base of the volcano, but then they're opening up a new area down at the caldera where I showed you where we put in the GPS. And then we have them going over here again between this is Chiles here again, and then here is between the 2. And the most recent swarm has been at the base of the volcano. So that's why I use the word flip-flopping, because how do you know where it's going to go? We don't know yet why it goes from one to the other. So one of my colleagues who works exclusively almost on this, on due to seismicity here, he located these 40,000 events, and that's from 2013 until now. And basically the lilac color deals with that which is at the base of Chiles volcano, and then this area is the other nest over there. So we have these 2 competing areas, and right now, this area is the one that's in operation. the lilac colored one. So getting to a little bit more, here you see the two different nests. And what's notable, as I said, is the abrupt onset from basically not having any activity to just going way up, way up. It's like you have a little hose that's garden hose, and then all of a sudden you have a fire hose of water. So these are earthquakes that are just happening constantly. And this period, this last period, then in 2022, produced another 5.6 earthquake right over there. Okay. So that earthquake looked like this on the in GCENT and also on the Comet webpage, a very nice concentric rings. You can see it was a strike-slip left lateral on an east-west blind fault right there that had never been identified. This fault had never been identified. It had about 10 or 12 centimeters of offset. In the area where the quake occurred, there were lots of landslides, but nobody could actually find the real, like the fissure in the ground that you can sometimes find. So, and then this is a 2023 earthquake swarm, which is dipping to the east here. And you can see that this little fringe up here and this little thing is a shallow. Those are LP events. The majority are all VT fracture quakes. And some of them, as we see, are up to 3.4, 4.3. And then these others here are LP. So this period draws our attention to this number of shallower quakes that occurred. I wanted to show you then some of the GPS velocity registry that we have, and that is that covering, this is only the last 60 days between March and May of this year, and this is representative of the recent trends of this year. So what's interesting is that this particular station is going northeastward, this station here is going southwestward, and this station is going southeastward. So this is a very definite pattern. We only have 5 stations in the zone. This doesn't show anything. You can see the red is the vertical, and that's only in the last that's in 2 months between March and May. So it's quite definite, the patterns. And in this case, the station that we just saw that had the strongest pattern is this particular one. And this is the vertical right here. So you can see that recently there's been times when it was quite abrupt. The ascent, the rate of ascent was very abrupt between May, and that was coinciding with the swarm here and with the swarm here. So every time there's a swarm, there's a really strong, in this case, uplift. So. And then on the north and the south, we see that this is moving up to the north, like I said, and this is going to the east. So this is that's that, and that's that, and that's that. So why is that? It's probably because in the INSAR, we also see, this is on the vertical component, we also see these 2 areas which are mimicking very well what we see with the GPS, although the GPS doesn't cover the entire area perfectly, but we have a station there, we have a station there, we have a station there, and we have a station there. We do not have a station over here, which would be ideal. But anyway, we're able to see that there's these 2 very, very apparent zones of uplift. And we also see that in the preliminary modeling, and I say very preliminary modeling, with 2 different programs, this is a SARScape, I believe, and it shows that there's possibly a dike uniting the 2 areas. That would be about almost 18 kilometers long and about 8 kilometers below the Chile summit. Chile summit is 4,600 meters, so it's about 4 kilometers below the ground surface, the actual ground surface. And this is the quake that happened there last year in 2022. And then another solution was done, and it showed that approximately, again, the same dike, but this was using only in 2022, this particular station that we had over here. Since then, we put in another station there. and it's only a year old, so it's not mature yet. And so, as I said, as we get more maturity on our data series, then we're able to do a better modeling of these. But the INSAR also has a certain bad coherence in this area because of the earthquake. So the volume changes are very uncertain. It goes from 3 million cubic meters to 30 million cubic meters, which isn't a very good constraint whatsoever. So as I wanted to point out, the blue is related to this line here moving to the north, and the orange is related to that area here, so that's moving to the south. So we have a breaking apart. Literally, it's kind of everything's moving apart as if it's being torn apart. And again, we should put a station down here. So putting it all together in a graphic summary, we have these two swarms that have operated now on 3 occasions, but particularly right now, it's dying down, but it's been recent, since May, and or March rather, and we see that this is literally being pulled apart up at the northern part, and this southern part is also going at least to the right. We can't say so much to the left. It's had 2 different earthquakes, 5.6. And we can see, in terms of looking at the long term, this is what we have in terms of the GPS, going from 2014 all the way up to a couple weeks, or just last week, that we now have almost an accentuation since 2022, which is the same time we've had this very, very strong earthquake activity. So summing up, what does it look like that we have? We have a metamorphic basement around 10, 15 kilometers depth. We have probably, as I showed you, the faults, which are bringing up probably hot fluids. But on the other hand, there might be seals in there. There's been some deep drilling, but they've only gone down 4 kilometers. That is for geothermal purposes. There are hot springs there. They're frequently monitored, and there is no significant changes. I remember what Michelle said. There's no significant changes in the mixture of the gases. Okay? There's multi-gas. There's all these other ratios being done, not by myself, but my colleagues. There's no changes. There might have been a change of 2 degrees centigrade in the last time. They have to reconfirm that. But there's 3 or 4 hot springs there. There's another hot spring there, but there's nothing really big happening at the moment. And these LPs happened up here 2 to 3 kilometers below the actual ground surface. The deeper VTs are happening about 4 or 5 kilometers below the actual surface, so maybe 8 or 9 kilometers below the summit of this volcano, and also below this area. So we think that seals have, or that is some kind of a cap that is formed. It does not allow a great change to happen in the surface yet, and that's what's creating, the pressures are coming up, but they're not able to get through, and these VTs, which are actual VTs, are happening. So the conclusions is that this incipient deformation is a precursor and is synchronous to seismic swarm reactivation. And deformation continues at Chile's GPS right now, even after the swarm activity ceases. Seismic nest activity occupies areas next to old dormant volcanoes, and that VT events are concentrated 4 to 8 kilometers below the Chile summit. They're not on the surface, they're down deep. It's not like a hydrothermal system that's within drilling of the top of the surface of the land. And it's probably down in the metamorphic basement where magma there may be body or storages in there. And magma bodies are pushing upward. That's a hypothesis right now, creating this notable deformation. And it's detected, as we saw by the INSAR and the GPS. And therefore, if in the future the magma ascends closer to the surface, that is, if it could break seals in disrupting the hydrothermal system, like we see that it's happened, for instance, at Yellowstone or maybe Campo Felibre, then deformation may accentuate, and spawning of hot springs and geysers could happen in new areas. That hasn't happened here. We're waiting. And therefore, none of these changes have occurred. And the 2 5.6 magnitude earthquakes in 214 and 222, both on the perimeter of these seismic nests and deformation halos, are likely or may be the result of the disruption of biomagnetic pressures of the stress fields, magnetic pressures that are driving these VT events, driving. I mean, the stress fields of local faults, leading to rupture of these faults. One which we didn't even know about, the other which you can see on Landsat, okay? And basically, as I showed, the preliminary modeling by GPS and INSAR suggests that a dike may be in place, or it's trying to be in place in the direction of northwest, southeast. And it's a hypothesis coherent with the vectors of the main GPS stations, as we saw the breaking apart of at least the two northern stations where we have the stations, and leading to rupture of these faults. And the pyroclastic deposits of past eruptions were water rich, had a high silicon content of approximately 70% SiO2. They were explosive and occurred 15 to 20,000 years ago. So that's the end of my story for now. And we'll be working on it, but I just wanted to share this little tidbit with you to get any feedback, criticisms, or observations. Thank you very much.
Well, yeah. Well, we're a few minutes beyond, so we're gonna have to save questions maybe at the end. And so we need to move on to the next talk, which is by Odysseus Papas, and it's on simulating satellite radar measurements of volcanic eruptions in preparation for ESA's Harmony mission.
Right, hello everyone. So as advertised, I'll be talking to you today about the Harmony mission and some of the work that we've been doing in simulating satellite radar measurements of volcanic eruptions. So I trust that a lot of you will be familiar with the Harmony mission, especially after a couple of very interesting talks about it that we had yesterday. But allow me to reintroduce it to you. Harmony is an upcoming mission, an upcoming satellite mission of the European Space Agency. It has been selected to be the 10th entry in the Earth Explorer program. And its mission really would be the observation and quantification of small-scale deformation. And there is a great number of scientific fields in which Harmony will seek to provide data and answer questions, and you can get an idea of some of them on this graph here. There's stuff related to the cryosphere, the oceans, the solid Earth. But of course, the one that interests us today in the context of this session is Harmony's ability to measure topographic change related to volcanic eruptions. Now, Harmony will be doing all this useful stuff by the magic of interferometric synthetic aperture radar. The mission will consist of two spacecraft, both of which will be equipped with a passive receive-only SAR instrument. And the two satellites will be orbiting in formation with Sentinel-1, in tandem, if you will. So what that will give us effectively is bistatic single-pass INSAR capabilities. And I'm sure you're all familiar with the benefits of bistatic INSAR in terms of coherence, in terms of the measurement accuracy and the overall performance that we get out of it. Now, over the lifetime of the mission, Harmony will be operating in a couple of different orbiting configurations, which have been designed to optimize specific types of measurements that Harmony will be acquiring. The ones we're interested in, namely this production of a dense time series of surface elevation models for evaluating topographic change after volcanic activity, those will be generated in this second mode that you see in the graph here, the across-track interferometry mode. In that mode, we will have the two satellites flying in a passively safe helix formation behind Sentinel-1 with a baseline, a distance between the two satellites that will actually vary a little bit as they go through their orbit. And this is something that I will come back to later on. But what you want to take note of right now is the fact that different parts of the Earth, different volcanoes that are located in different latitudes will be imaged with a different baseline and therefore slightly different performance. Exactly how the baseline will vary, of course, is still something that is being designed, but it will vary probably from about 500 to about 800 meters, like you can see in the graph there. Now, in terms of the topographic change that Harmony will seek to image and quantify, It can be quite varied scenario in itself because, topographic change and volcanic eruptions are quite varied themselves. We have instances of lava flow and deposits of lava. We have instances of pyroclastic flows. We have growth of lava domes, and in occasions we have collapse of lava domes, or possibly even entire flanks and edifices of the volcano and the surrounding topography. So what we tried to do here in this body of work was to perform a sort of case study where we took high resolution bistatic INSAR data. Specifically, we took TandemX co-SSE data, and we tried to look at a recent volcanic eruption and produce an interferogram, a set of interferograms and topographic change maps for that eruption. The goal here was to demonstrate some of the particular challenges of dealing with INSAR and volcanoes, and I'm sure you're all familiar with the effects of the very steep topography that we often see in these kind of scenarios in combination with the viewing direction and the general viewing geometry of the radar. Effectively, things like shadow and layover can become a really detrimental factor in the DEMs, or topographic change maps, that you produce. And we wanted to demonstrate the challenges and demonstrate the need for a sort of qualitative assessment and possibly masking of any DEM or topographic change maps that are produced. And also, of course, to show the importance of having both ascending and descending acquisitions over volcanic regions of interest, because, again, as I'm sure most of you know, these things like shadow and layover, they're dependent on your look direction, and as that is reversed, whether you're on ascending or descending orbit, it leads to a situation where you kind of need both in order to have a complete and clear picture of what is happening at a volcano. Now, besides demonstrating these points as part of the science mission, we also wanted to generate these high-resolution topographic change maps as a product to be handed over to our colleagues over at DLR, the German Aerospace Agency. So they have been tasked with developing, or rather they have developed by this point, an end-to-end simulator for harmony. If any of you were at Paul Pratt's talk yesterday, you heard about Heaps Terra. And in modeling what harmony's output would be in such cases, they require data to serve as input topographic change, as ground truth. And the stuff that we produce here could serve for that purpose. Now, of course, the kind of elephant in the room is the resolution, because we know that harmony is not going to have the particularly high resolution that we have, say, with TandemX. So there's this obvious question of what exactly will the data from harmony look like. As an illustration of the importance of resolution, here we have an example of a DEM and a top map from a relatively recent period of dome growth in St. Helens. And in the original data, which was at this very high resolution of 1 meter, you can see some very interesting features that you can still pick out if you subsample that data to 20 meters, but if you were to bring it down to 50, they're completely gone. So we were wondering what harmony's resolution and data would look like. So what we decided to try and do, and this is completely separate from the end-to-end simulator that I mentioned just before over DLR, but we decided on our end to see if we could somehow subsample our data, our high-resolution TandemX data, to something that would be more in line with harmony and Sentinel-1 effectively, because they're inherently tied, and see what that perhaps might look like. So we took as our case study St. Vincent La Soufrière, where we had a recent eruption beginning in very late 2020. There was an effusive eruption during which we saw the formation and growth of a new lava dome. From April 2021, we had an explosive eruption, and by the end of that eruption, we saw the complete destruction of both the new and the old lava domes, as well as the formation of a new crater and the deposition of tephra along the rim of this new crater. Now, in this graph, you see a timeline of the events that happened over the eruption of St. Vincent, and it's actually here to illustrate one of the great advantages, one of the more exciting features about harmony, that is harmony's temporal resolution. So on this timeline, you see these dots, which correspond to measurements of dome growth, which were performed using a drone flights on the ground. And you can see they're quite sparse, and they become very sparse to non-existence as you go further down the timeline. Now, one of harmony's most exciting features really for this kind of study is the fact that it will be producing DEMs at a regular 12-day interval. So if it was operational over a timeline of interest like this one, we would have gotten at least a dozen DEMs produced over this period, which is quite great in terms of being able to monitor the different stages of the event. Unfortunately, Harmony is not quite yet doing that. So we used TandemX co-SSC data, and we only had access to 3 products. There were 2 pre-eruptive products and 1 post-eruptive product. There was nothing available that covered the actual period of dome growth. So again, you can compare and contrast that with the picture that we just saw of the 12-day acquisitions for Harmony. But nevertheless, this is what was available and what we worked with. So we also needed to have some sort of underlying DEM for our study. And the obvious candidates would be something like SRTM at 30 meters, globally available, could be used for any case study of interest. But in this particular situation, we also had a much higher resolution DEM available. It's a DEM recently made using Pleiades optical imagery with some gap filling with Copernicus data. So that one is a 2 meters resolution, and most of the figures that I'm going to be showing you today are using this high resolution DEM, though we did repeat our experiments also with SRTM and a few other things. So we took our TandemX single look complex pair of images. We did our interferometric processing in gamma. It's fairly standard stuff. We got our interferograms, removed topographic phase, unwrapped them, generated our height maps, geocoded them. Again, fairly standard stuff. And this is the kind of results that we got. So we have the pre-eruptive data up at the top. We have the SLC of the region of interest of the volcano. And for every pixel in our area of interest, we evaluated ground resolution and height precision of the produced DEMs. This was done as a means of quantifying the quality and the accuracy of the DEMs at every pixel. It's actually based on work that Fabian has done before. And we can not only quantify the quality of the DEM, but we can also use it to mask out areas of low quality by setting in an ad hoc fashion thresholds that we do not want to exceed in terms of resolution precision. And you can see an example of that in the topographic change map for the pre-eruptive case, where we would normally expect to see pretty much nothing at all. It should be in good agreement with the pre-eruptive DEM. But you can see obviously this large deformation there that is very clearly because of shadowing effects in the original image. It's a completely erroneous measurement. But if we decide to mask out these pixels of low quality in the DEM, as you see in the grayed out pixels over to the right, we can effectively eliminate those or exclude them from any calculations of further analysis. In the bottom, of course, we have the post-eruptive case, which is the more interesting one because we actually have a view of the topographic change that took place, and we can see it actually a little bit better here. So what we were able to see with the high-resolution TandemX data is a picture that appears to be in pretty good agreement with what has been reported as happening in St. Vincent. We saw the complete destruction of the new lava dome. There's nothing there. There's a new crater formed, this large area of subsidence in the center, subsidence being in red here. And we see the deposition of tephra with 2 noticeable lumps on the north and south of the rim of the crater. Now, this topographic change map, as I said, was also passed on to our colleagues at DLR to serve as input for their simulator. But we wanted to see if we can simulate Harmony's resolution on our end as well. So we decided to try and subsample our data. Now, we didn't want to subsample the produced topographic change map. We wanted to subsample the original SLC products to try and get single look complex images comparable to what Harmony would be getting, which again is comparable to what Sentinel is putting out. And we wanted to reprocess those through gamma. Now, the subsampling, we didn't want to simply multi-look the image because that would give you aliasing artifacts. So the subsampling was done in the frequency domain to avoid aliasing artifacts and to create a low resolution subsampled SLC, which I'm referring to as HRM20 in these figures, just for shorthand. It is at 20 meters resolution. And these are the experiments, again, now repeated with these lower resolution SLCs. Once again, we have our ground resolution and our high precision maps, which we can use to mask parts of our topographic change maps that are not of particularly good quality. And if we look at the post-eruptive case in this situation, we see a picture that does include some subsidence where the crater should be, though it is somewhat misaligned, as we've noticed. And the The uplift due to the deposit of tephra is still there, but it's of a lower magnitude than we expect it to be. We noticed a similar situation regardless of what the underlying DEM for measuring the topographic phase and for geocoding and everything was. And we know it's not a fault of the DEM. If anything, moving to something like SRTM, which we then found out had some errors in this area, actually caused more problems than we had before. And we are fairly confident that this is down to an unwrapping error, because this is a particularly challenging case of topographic deformation and terrain. And unwrapping the full high-resolution data was already fairly challenging on its own right. So we're thinking that in the low-resolution case, it basically became impossible to delineate the fringes accurately, and that's why we had these results. So one of the main things that we're focusing on now is trying out different unwrapping strategies to try and see what might perhaps be the optimal way to tackle this particular kind of challenging situations. The good news, on the other hand, is that our colleagues over at DLR, who used these topographic change maps as ground truth as input for the simulator, were able to get results out of their simulator that are much more in line with the original ground truth data, albeit obviously a little bit noisier, a little bit lower resolution, but generally, a much better picture. So that kind of puts more the onus on us to try and work out something better in terms of unwrapping our own data. So the work that I showed you here was primarily work that we did last year, and recently we acquired some extra funding to continue working on this. And as I mentioned, we want to be looking at a few things to improve the performance of our Harmony 20-meter simulation method, particularly when it comes to unwrapping. But also we want to extend our work to a couple more case studies. The first candidates that we're going to try and tackle are Reventador and Fuego. These are not only volcanoes that are in different parts of the world and therefore in different latitudes, imaged under different baseline conditions and so on, but also they exhibit different types of topographic change. We've got lava flows and pyroclastic flows, respectively. And there are also volcanoes that other people in the group have studied in the past, so we have some experience with that and with these particular cases and data already available in-house. So I will leave you with that. I'd like to thank you for your time. Obviously, if you have any questions, I'm more than happy to answer them now or discuss them later. There are, of course, some references to some of the stuff that I was talking about earlier and some of the graphs. And once again, thank you very much.
Thank you. Do we have any questions? Can you get the microphone up? Maybe?
Sorry, thank you. Thank you for the talk. I was wondering, so you talk about like the improvement will be probably to work on the unwrapping. Do you have already some ideas or what you're going to test for the unwrapping stuff?
Yeah, the current unwrapping strategy, because as I said, we were working with Gamma, so we were using the minimum cost flow algorithm within Gamma. We want to try out a few other things. Well, some of the obvious candidates obviously being SNAFU. That's actually what I'm working on now, trying to interface the data with that to see if it's any better. Then there is the new Lixo tool that Milan can probably tell you a lot more about, that I would like to try out at some point in the near future. And, you know, I don't know if we're going to have time within the context of this project to look at maybe more exotic options like novel unwrapping algorithms or anything like that, but possibly in the future. But the immediate candidates, as I said, we're going to try and look at SNAFU and Lixa. But of course, if anyone has any suggestions of things that, you know, are perhaps particularly well suited to dealing with these kind of challenges, I'm, you know, I'm all ears.
And just a small question about the, so here, because of TandemX, you'd only have one before and after, which is a very sparse data set to test. I was wondering, of course, if we, with Harmony, we expect to have 12 days, that one of the solutions will be like stack of, if you can stack pre and post DM, and if it's something that can be tested via the end-to-end simulator, like.
I'm not 100% sure off the top of my head if the end-to-end simulator at this stage can do stacks.
Okay.
But then again, you know, PowerPrats is probably a lot more well suited to answer that. I do though think that the simulator will be available for use very soon. So that is hopefully something that could perhaps we could try out by simulating data in there. Yeah.
Okay, thank you.
Okay, thank you very much. We'll move on now and have probably time for questions, maybe towards the round table at the end. Any speakers? The next speaker now is my co-chair, Paul Lundgren, who's going to be talking about volcano science applications, observation needs from future topographic missions.
Yeah, so this is, so yeah, it was good having that Harmony talk. So this is something that's even further in the future. It has no mission yet, but I'm going to talk about STV, which stands for Surface Topography Vegetation. And we're doing a volcano-related sensitivity analysis study for this. And I have a number of co-authors and collaborators. Alberto Roman is leading the modeling of the flows right now. And then in the future, we're going to be incorporating data sets, including St. Vincent with data from Rafael Grandin and his group, and possibly other data to guide some of the simulation studies we do. So, so you might be wondering, what is STV? So NASA every decade has what's called the Decadal Survey that's conducted by the National Academy of Science, Engineering, and Medicine in the U.S., and it places guidelines on NASA Earth science for the next decade and what missions should be developed, what, et cetera. And in 2017, something called STV was designated as an incubation observable, so something that wasn't, the technology was not viewed as being mature enough in the current decade, but was to be, NASA was to invest in science and technology studies to advance that, such that in the next decade, post 2027, it might be ready to be kind of put on board to become a mission. And so as part of that, they had a one-year study team that developed a 200-odd page document about what, you know, to guide the next decade of investments for NASA. And so we, you know, as part of that, there was, and this is over, of course, the full range of solid earth, vegetation, hydrology, et cetera, anything that might need topography or vegetation structure and topography as well. And so they have, you know, they developed this entire range from science to technology development and identifying various types of gaps. And so what we're focused on here is what we call the knowledge gap, which is really the question, and we're focused, of course, on volcanoes, is really what are the science needs for volcanoes, as opposed to, you know, typically what we do, I think, is we see the highest resolution data, as in the case, say, for St. Vincent, and we say, wow, that's really great. But what we wanted to, from a mission perspective, one of the things in theory, we'd like to do is use what are called OSSEs, observing simulation system experiments, to basically have the science drive what the observation needs are, rather than saying, well, we've got a particular technology, it gives us this, tell us what you can do scientifically with this. And this includes both the observations themselves and also the architecture for the mission. And so what we're doing in this study is we're really trying to understand these volcano topography needs through a series of different types of simulations. One is for dynamic volcano models, so models that connect subsurface magma dynamics and diffusion. What are the needs from the diffusion part that along with geodesy would help control parameter estimation in such models? So what do we need for that? Then there's, of course, as you can imagine, there's for hazard forecasting, for flow modeling for different types of deposits and avalanches, etc. What are the resolutions you might need for those types of applications? And then finally, how do these things, what are the implications for mission architectures, which includes temporal sampling? And so just in some graphics, what this means is we're really trying to use some exemplary data sets, such as St. Vincent, such as in Hawaii and other places, also in the Western Pacific, and how can we connect these to these different types of either physics-based models, flow models, and observations, and more on the hazard side of things. And so right now, today, I'm just going to talk really about the flow part and connecting it with a simple flow model that Alberto Roman has developed, and he has a poster on that. And so just again, we're looking at, again, the surface, looking for flows. We're looking at the Kilauea flow forecasting, and that's what we're doing right now. Eventually, we'll be doing other analyses for different systems, and then eventually the dynamic model implications. So in terms of, so one of the areas that we're looking at is something we looked at before with Kilauea volcano, where during the 2018 eruption, we had flown the year prior with GLISTEN, which is an airborne bistatic Ka-band radar that flies on a G3 jet, and we could do, it does 10-kilometer wide swaths of arbitrary length, and we could cover in fact, the entire flow field with one swath, but we actually had many swaths in different directions. And we also, of course, there was the caldera collapse as well. But we're going to focus here on this. And so we had a GLISTEN acquisition before, but we also had we were very lucky in 2018 to have a bare earth DEM, LiDAR-based DEM that covered this area. You can kind of see the edge of it right here. And then for the other areas, we had a Tandem-X 12-meter DEM. So if you difference the pre-eruption GLISTEN with the LiDAR, because GLISTEN being Ka band is sensitive to the top of the vegetation, you essentially have a vegetation height mass. And then as you go into the eruption and you difference that with the pre-eruption GLISTEN, you get something like this. But of course, where the lava goes through forest, you get negative topography, so negative thickness effectively. And so, but in the end, when you add these together, you get the final flow field. Now, of course, the key thing here was we actually relied on HBO to provide outlines of the DEMs because the data is noisy enough that you can't independently really select the outlines of that. So we had to cheat a little bit, which I think down the road will be part of the implication, I think, for any topography mission is to what extent do you need independent data to define things like flows versus being able to rely completely within the data that you've collected. And so again, this just shows the data that we had over time. And you get, if you look at the last 2 days, of course, you get nice things and the channel is filled, and after the eruption, it drains out. So there's some other interesting details that we're not going to probably be able to explore in our own simulations, but I think the key thing is that there are things that we can model, and then there are things that we can't yet model, and we have to try to understand also to what extent we need to be able to measure those as well. So some things like that might imply a higher resolution than maybe the simulations themselves require. So here I'm just going to talk about the flow model that Alberto has written this summer. It's a simple flow model with a single viscosity. It's isothermal, and yet we think that the first order captures kind of the main works to first order. And we're not, we use Kilauea kind of as a kind of proof of concept that, passes the smell test, so to speak. So it's reasonable in that extent. And again, as I mentioned, it's a simple nonlinear PDE that's solved, and it has both the topography gradient and the flow thickness coming into this. And so it captures both convection and diffusion. And so we can run these for different topography resolutions. So if we take the original, and this is just 4 hours. It's 4 hours of model time. It took only a day to run this stuff on my laptop, so it's not that fast, unfortunately. But if we take the original LiDAR bare Earth DEM and resample it at 5 meters, you get a solution like this. If you resample it at 25 meters, it turns out they're different, but they're not that different. So, the first thing that we seem to be seeing with these kind of flow models is that, the question is how sensitive are they to the actual resolution, and we don't know the answer yet, but it does seem that it's varying dramatically with the resolution at these scales anyway. And of course, this is with a particular, there's also questions of, this is with 120 cubic meters per second and a viscosity of 10 to the 4th. So, these things can vary with the physics as well in the solution. And so as I mentioned, that's kind of the proof of pass the smell test if you can fit Kilauea, or when we move to domes, if we model St. Vincent or other places, that kind of serves as a guide to what we put into the model. But what Alberto's doing right now is a more systematic approach of looking at taking, say, something very idealized, like just a planar ramp, and with some there we go. So the question is, if you take a planar ramp, you add some noise to it, what are the effects on solution? So in this case, you've got a ramp that's dipping in this direction. If you have no noise, of course, you get what you would expect, and these have been benchmarked to analytical solutions for simple cases. But when you add, in this case, half a meter of standard deviation in the noise, you get, it looks pretty similar. There's a little broadening, but it's also retarded in time. So there's a delay there. So that's another aspect to consider, is because when it comes to, actual, for the USGS or somebody that's trying to predict flow advancement, understanding that there would be trade-offs in topographic noise versus, whatever parameters you have to put into the model to try to fit, where things are at a certain point in time in order to maybe predict where it will go and how fast in the future. And then, of course, as you go to higher amounts of noise, things start to break down a bit and get somewhat interesting, but again, it can have a deteriorating effect on the solution. And so finally, the other thing that Alberto's played with is putting in some obstacle. And when you do that, of course, it goes around the obstacle. But again, as you have as you add noise to that, it both degrades the solution and causes some delay. So in terms of both the spatial aspects of the DEM and then the eventual temporal sampling you might need in any future observing system. Those are the kind of things we're trying to explore. And so with that, so the key takeaways are that, this is something we've really just started, so we don't have any real, meaty results yet, but we'll be presenting a little more at AGU. And so again, as I just showed, we're looking at these simulations to try to understand the effects of noise levels, coming up with metrics whereby we can assess both on coverage and thickness. There have been a lot of studies where people have been looking at trying to understand the fidelity of different flow models to existing flows, observed flows, and how well they perform. And usually that's done in terms of the spatial coverage, how well it matches that. But we have to consider thickness as well as important. And then, as I mentioned, time will be another aspect to this. And another thing I didn't get into is then when you have these, in the case of Kilauea in 2018, of course, new flows will impact where the next fissure outbreak is and where its flows go. And so that's another consideration, not so much in terms of the fidelity of matching, of modeling the next flow in terms of if you used an old DEM that wasn't updated, but it certainly implies that for the mission, if you want those simulations to be accurate, you would need to be updating your DEM accordingly. And then, as I mentioned earlier, just other things that we're kind of not considering yet, but might become important are things like flow boundary detection. Can we do that independently of bringing in some kind of optical or other kind of imagery that would be independently used to define that? And then, of course, eventually, one would like to have increased physical realism in the models, but for now, we think there's a lot to be gained just in terms of relative simulations based on this relatively simple physical model. And so the final thing is, I would encourage you to go see Alberto's poster, which for more details and for a more thorough explanation of the method. And with that, thank you.
Okay, thank you. Are there any questions for Paul? Well, I can ask a question.
Okay.
So the simulations you showed look to be very much like shield volcanoes like Hawaii. Do you think it would make a difference if you tried this as stratovolcanoes, a very steep-sided, narrow drainage channel? The resolution of your topography might make more of a difference?
Well, that's one of the things we're going to be exploring. So we started with this, and of course these are I mean, I think that, so the more viscous the flow, in some ways, the less likely less sensitive it might be to kind of very high frequency topography, whereas very thin, low viscosity flows might be more easily deflected. But another thing that we're also want to consider is, and I think it's important for physics-based models, is when you get the case of very small domes, when they're just starting, so the surface, the area that it covers might be quite small, then I think resolution might be more important, whereas, of course, if it gets bigger, you can have a slightly coarser resolution in your DEM potentially. And so, and of course, in these physics-based models, in the beginning, the trajectory is very fast potentially, and that could be more critical potentially for future prediction of where the system will go. So,
any other questions? Okay, in that case, we'll close the session and have some coffee, which you all look like you need, and then we will be back at 4:10 for the Volcano 3 session.
It's great being in the harmony.
Yeah, very nice. So perhaps
Right, so I think we'll start now. This is the final session. We've had one talk pull out, so we're moving everything forward and we'll have lots of time for questions and discussion at the end. So first off is Juliette Bates, who's missing bits of slide. Will you take a minute?
no, it's just that slide. You don't know why the other ones look okay. All right, we'll just keep going. And if there's any other, if it happens again, I will tell you what's missing.
Okay, I'll give you 2 minutes, but you can take your time.
Okay. All right. Okay. Thank you very much. So I realise, to my horror, that this is almost exactly 20 years since I first came to Fringe. And back in those early Frascati Fringes, we spent all our time asking ESA for more data. And actually, look what happened. They gave us a lot more data. So the LIXAR volcano database, Sentinel-1 INSAR data, now contains over 2 million different images of volcanoes, and that spans more than 1,000 volcanoes around the world. And this presents remarkable opportunities for understanding magmatic systems on a global scale, and also for monitoring and forecasting in the short term. But there are lots of challenges associated with the basically the size of the data set, particularly to do with expert interpretation and timely dissemination. And a real theme of this Fringe meeting has been people turning towards machine learning and deep learning tools in order to address these challenges. So what I'm going to talk about today, and actually the next couple of talks following me, are all about some of the machine learning and deep learning methods that we've been developing within COMET, and I'm going to talk specifically about the ones we've been developing at Bristol. And the talk is divided into 2 parts. The first one is really now an operational system. It's a convolutional neural network that we developed with Pui and Fabian back in a series of papers in 2018, 2019. And I'm going to update you about what we've been doing to deploy that on a much larger data set and in an operational sense. And then the second part of the talk is introducing you to some new methods that we're developing, new architectures, new applications, and new catalogs. And these are very much in the proof of concept stage. These are a long way from becoming operational. So a quick recap of this deep learning framework for the detection of volcano deformation. So it's based on a transfer learning principle. So there are lots of networks that have been developed and trained extensively for looking at photographs. And a favorite task is identifying pictures of your pets. So this particular one I'm showing you here has the probability of this picture being a probability that it's a picture of a dog versus that of a cat. And that's not terribly useful for our particular application, but what we can do is we can take away this upper layer and we can retrain it with some information about volcanoes. And we found the best way to do that is a combination of real examples, real interferograms, and synthetic examples of what we think both deformation and noise really looks like. And we also need to have a balanced training data set that has both positive and negative samples. So this training process is pretty slow. It requires an HPC, but once you've got the model trained, you can actually apply it to large numbers of images very, very quickly. And so what we do is we divide our interferograms into patches, we run those through, we merge them back together, and we get something that looks like this. So in this image, we have an interferogram shown in grayscale. The yellow colors represent the probability according to the CNN, and we have contours at probabilities of 0.5 and 0.9. So this was developed on a LIXAR test dataset, which consisted of about 30,000 interferograms. It seemed huge at the time. By 5 years later, it actually seems fairly small. But we had a classification accuracy of 0.981 and a detection threshold we estimate to be something like 3 or 4 centimeters, depending on the conditions. So basically, you need a couple of fringe or more to be able to do this. So what I'm going to talk you through now is how we've tried applying this on a much larger scale, and there are 3 steps here. So the first one is the automatic processing needed to provide the data set. The second one is the detection, and the third one is the expert review. And don't try and read all this because I'm going to break it down. So the first bit here is the automatic processing, and we're using the LIXAR system, as you might expect. And what I'm going to show you is a much larger data set than the proof of concept one. It consists of nearly 600,000 images spanning the first 5 years of Sentinel-1. And what's important here is that it has a much greater global coverage than our proof of concept data set did, and also that it now includes some long-term interferograms, which turn out to be really important, as you'll see later. We then run this CNN through the data, and it flags up 3,000 images of 366 different volcanoes. So this is a positive rate of less than 1%, which is actually, we've really reduced the size of the data set that we have to look at, but it's still quite a lot of images to look at, and that's only going to increase with time. So we need a strategy for dealing with this. And what we do is we look at the number of positives per volcano, and that's what the histogram here shows. And there's a kind of a natural divide here at about 25. So the volcanoes with more than 25 flags tend to have very high probabilities. There are 16 of these. And the volcanoes with less than 25 flags generally have lower probabilities. And we can treat these 2 types of behavior in different ways. And I should also say we throw out any of the flags that use only 1 flag per volcano. Because of the redundant way we do the processing, any real deformation signal ought to get flagged 6 times. But we throw out anything that only occurs once. So once we've identified these volcanoes, we can look up external information. The GVP, for example, records information about seismic swarms and other kind of changes that might be observed at the volcano. We can look that up. But also for the persistently classified volcanoes, we can carry out time series analysis. So the actual displacement time series is shown here in blue, but we can also run each epoch of this time series through our CNN and find out where the flags actually start. The examples I've shown here are 2 eruptions, and the red time series, which is the probability from the CNN, clearly jumps up at the time of the eruption. And we can also apply some atmospheric corrections. So when we were doing our proof of concept studies, one thing that we found very effective at distinguishing between false positives and true positives was using an atmospheric model. It's the one thing that really still confuses the model in some cases. So the example I'm showing here is from Fuji, which had a lot of detections. And actually, if we look at the time series, you can see it's clearly very seasonal. If we apply a Gakos correction, we reduce both the seasonality and the number of detections. So this is what we think of as a false positive. So what did we find? Well, as you might expect, the data set is dominated by large deformation events. And in fact, it's almost completely dominated by the Galapagos. Over a third of our detections come from there, including over 900 from Sierra Negra. So there's actually 2 reasons for this. One of them is there are a lot of actively deforming volcanoes, as Susie showed us earlier. But also, it's a wonderful natural laboratory for INSAR, so our LIXAR data set is really up to date. And so there are an awful lot of interferograms in this area for us to look at. But we also detect some other eruptions and intrusions, and between them, Kilauea, Tal, Etna, and Artele account for another 150 of these flags. But we were very happy that we could actually start to detect slow deformation events that are not associated with eruptions or intrusions. And these 2 examples are Laguna del Maule and Demoyo, which are slowly deforming volcanoes in the high Andes. The reason we can detect these is because we now have these long duration interferograms. The figure at the bottom here plots each one of these images according to duration and coherence, and the color of the dot represents the probability output from the CNN. And you can see all of these flagged interferograms are these long duration summer to summer coherent interferograms. So they're really important for picking out these slow deformation events in our data set. So just a quick recap of some of the other signals that we picked out that might be of interest. So Tambora here, previously no deformation had been reported at this volcano, and in fact ESA has stopped collecting data over this track, bizarrely in the middle of 2018, but we actually see subsidence of 8 centimeters a year, and this is actually quite significant. This is the site of the largest known historical eruption anywhere in the world, so this is quite alarming, and actually the time series has now been continued since then. And then we found Reykjanes Peninsula was flagged in quite a few, or flagged many times, actually for 2 reasons. One of them is the pre-eruptive signal for what is an ongoing eruption there, which we caught before the eruption started, and also the geothermal plant was flagged a large number of times. But we also detect non-volcanic sources that generate fringes. So Rinjani here, the reason that was detected wasn't actually anything to do with the volcano itself, but there was a nearby magnitude 6.9 earthquake that caused a lot of detection. And at Kjærfjord, actually the fringes we see are the ones associated with the edge of the ice cap rather than anything volcanic. So this system now runs automatically on every image processed by the LIXAR system. The big frames get processed, the volcanoes get cut out, and the system automatically runs a CNN and outputs a probability. And that information is shared through the volcano deformation portal. So if you go to the front page, you can see a list of the most recently flagged volcanoes here. And I did this just last week. Kilauea came up top. I clicked on Kilauea. It gives me a time series over here of all the different probabilities. It gives me the mean and the maximum. So I picked out a couple of times to show you. This is one here where there were a large number of flags, and you can clearly see the deformation signal that's picking up. And this is one where there weren't any flags, and you can see why there's nothing very interesting here happening. So this system, I would say, is now pretty much operational, but it's not perfect. So what are the next steps? What else can we do here? Well, one of the challenges, I think, with this system is that it's trained based on what we think the deformation signals we're looking for look like. And we actually don't really have enough examples. If you consider all the geologically plausible types of deformation signals we've got, our sampling of that is actually very small. And we've got around that by using a combination of data augmentation and synthetic training. But ultimately, that is going to bias our catalog to looking for more deformation signals that are like the ones that we've seen already. So one thing we're doing is developing unsupervised learning. It's called anomaly detection. So in this case, what you do is you train your model to understand the noisy conditions at a particular volcano. So it understands what all the noise looks like in your signal, and then it detects if something unusual happens. So here we have the unlabeled training data set. I run it through your model and it learns the average features. Then you can put in some test images, and what it calculates, the loss function it calculates is the difference between these test images and the average features that it had of the data set before, and it can then flag them as normal or abnormal. If you want to see some examples of how well or how badly this works, then I encourage you to go see Robert's poster in the poster session tomorrow, or even in the coffee break. Another approach that we're using is semi-supervised learning. This is sort of a blend of these two. So in this case, we use contrastive learning, which we input in the entire data set, and it learns the characteristics of that data set. And then you can train your detector with a much smaller number of labeled images. And once again, if you want to see how this works out, go see Pui's poster in the poster hall and see if you can find out whether this performs better or worse than some of our other CNN. But we're also looking into other types of applications of deep learning. And one of them is that one potential application is denoising. So we've heard a lot at this conference about the types of corrections you could apply to your data. But actually, can we train a deep learning model to do those corrections for us? This is a very simple example. This is possibly not even proof of concept yet. But what we've done is train the model using some images before and some synthetic deformation. Then we run it through a UNet architecture, which has 2 decoders, one for looking for the deformation and one for looking for the noise. What we're showing on the right here is synthetic data, and it works very nicely on synthetic data, but we haven't really tested it extensively on real data yet. So this is our input ground truth, then we add some noise to it, we run it through the model, and we can actually see a nice clean output, and this is the noise signal that it's removing from that. So I think this approach has a lot of potential, but we need to do more work on it. And another thing that I think is a really interesting machine learning, but not quite deep learning application, is to separate out different signals. So if we take a step back and think about volcanoes, we know that most volcanoes have lots of processes operating at the same time. And a really classic example are caldera systems, where we have deformation associated with the magmatic system and deformation associated with the hydrothermal system happening at the same time. And there was a really high-profile series of papers back in the 2000s that tried to separate these signals using gravity. And they never really came to a conclusion about what deformation was magmatic and what was hydrothermal. But actually, we now have sufficient data from missions like Sentinel-1 where we actually have a chance of being able to separate these signals out because they have different patterns in space and time. We would expect to see different behaviors between them. And so Edna has been trying to do this with ICA, and then also a sort of a clustering algorithm here. This is Matt Gaddis's algorithm. And because we are trying to differentiate the signals based on their spatial patterns, our hypothesis is that the hydrothermal system is structurally controlled. So we would have a structurally controlled pattern, whereas the magmatic system is deeper and probably wouldn't. We run the ICA in a spatial mode. And these are three components that we pick out. The first two are still slightly mixed together, but we can see the magmatic signal, which is really dominant in the data set. We can also see some topographically correlated signal. But most importantly, we can see this signal on the right here, which this east-west structure comes out very clearly. And that is from what we know of the structure and the hydrothermal system at this volcano. That is the hydrothermal system that we're picking out, and it's orders of magnitude smaller than the magmatic deformation. So we can actually start to separate these signals based on their spatial characteristics because we have enough data with Sentinel to allow us to do that finally. And then I just wanted to say a few words about sort of the final aims of, why are we trying to do this on a global scale rather than trying to understand each volcano on a really case-by-case data basis. And actually, we've put together, I've been involved in several kind of compilations over the years based on metadata, and we've learned a lot about magmatic systems, their links to it, the statistical links to eruptions, and the architecture of magmatic systems by doing this. But these are all based on metadata studies. Everything was processed in different ways and modeled in different ways, and it's a bit of a mishmash, and that always limits the kind of level of interpretation you can put on it. So hopefully, by using these systematically processed, systematic tools, we can actually build a much better catalogue that we can use for things like identifying analog behaviours of magmatic systems that are really useful for forecasting and really useful for understanding the characteristics of the systems in a global scale. So towards that, we're not using the full global machine learning catalogues yet. We're using a really nice subset of data that was put together by Fabian Albino that covers the whole East African Rift. So this is still 4,000 interferograms, 64 volcanoes, of which 16 have high signal-to-noise signals. And we're trying to classify these in the way that you could put the data into a catalogue. So the first step has been to look at these in time, and this is work that Fabian published last year. So for each of these 16 time series, we fit two models, one linear and one sigmoidal. The linear represents steady state behavior. Sigmoidal is not really meant to represent any particular physical process. It just allows you to capture the magnitude and the duration of the signal at that volcano. And we fit both models to the data, and then we use AIC to judge the goodness of fit for different models because they have different numbers of parameters, so we can't compare the root mean square. And what we find is that of these signals, 6 are best fit by a sigmoidal model, which means they have transient deformation. 7 of them are steady state, and another 3 are actually linear with a seasonal component added on top. And we can extract the parameters from these simple functional fits that allow us to build up a catalogue. The final stage in this process, or the next stage, I should say, not final, the next stage in this process is to actually think about the spatial patterns of these deformation signals. Once again, this is the same data set from Fabian, and you can see that the hugely different spatial patterns here. At the moment, we're doing this by trying to extract the source parameters using an inversion approach. And if you want to see more about that, go and see Ben Ireland's post-it in the poster session. So that is my conclusion, and I should probably stop to allow for some questions.
Yeah, that's exactly on time. All right, thank you. Who has a question for Juliet? Can we get the microphone up to Paul's hand went up first? Immediately.
That always makes me nervous.
No, I just wanted to beat out the competition. No, so one question I had is, so these are being done for ascending or descending independently. You're not kind of cross-checking them?
Yep,
Because,
at the moment, we're just doing each interferogram, no matter where it comes from. And actually, for the operational system, we don't even care which volcano it comes from. It's just a whole bunch of PNGs. They could be from anywhere.
I was thinking that, you know, as humans, when we get something in a volcano,
Mhm.
typically you say, well, let's confirm it by looking at the other
Yeah.
track, just to
Yeah,
make
yeah.
sure, especially for atmosphere.
Yeah, and I think that probably is the direction we're going in. So we're starting to already compile the data per volcano, build time series, apply these methods to time series rather than individual interferograms. And I think building in multiple time series at the same volcano is a logical progression.
Okay, great.
Do we have one more question? Okay. Okay.
Folks' question was, am I looking at wrapped or unwrapped interferograms? For the CNN that I showed you, that is all wrapped individual interferograms. Some of the other methods I'm showing you are using unwrapped data and moving towards unwrapped data time series atmospherically corrected. But the original one, actually when we started doing this, we didn't have unwrapped data, we didn't have time series, so we started off with the wrapped interferograms.
Well, I think it's better to look at.
Well, absolutely, but it depends which model you're using, which works best. So our system was designed to work very well on those, and that there's certainly advantages to that. But for other systems, it's a bit better to work on the unwrapped data for sure.
All right, thank you, Juliet.
Okay, let's move on with Danny Huber. He will continue with machine learning and classification and forecasting.
Okay, well, thank you, Juliet. I think that's nice introduces my talk as well. So I'm going to talk about sort of moving beyond the detection and classification to forecasting, although I will touch on detection and classification as we go along. So this work is also under the banner of COMET, but I'm particularly focusing on the work that's going on from the Deep Fog team. So this is an EU project, EU-funded project that we're working on for the next, well, it's a 5-year project. We're a couple of years in already. As I go along, I'll just be sort of flagging up other people's presentations and posters that you can go and get more detail from. Okay, so this was kind of motivated by the field of video prediction. So this is a computer science field where people could take a couple of frames and then predict what happens afterwards. So in this example here, it's not our example, it's just one I'm taking from the web. But just the first couple of frames here are used to predict, right? So when it goes yellow, that's already a prediction. So you can see just the first couple of frames are used, and then there's several different models here showing how a human continues to run across the page. Okay, it's not perfect, but it's doing quite a good job. So it's motivated by that, and you might ask why we want to bother to try and predict deformation or forecast deformation. It's mainly as a tool to be used by volcano observatories. So it's an extra tool that could be used to maybe inform what may or may not happen. So in principle, if we have a database of actual deformation maps from INSAR, we can feed them into a deep learning network of some sort and train that deep learning network. And then during a forecasting stage, we can take a whole bunch of recent deformation maps, feed them in, and then the deep learning network will spit out what might happen next. So this is a case of real data where there was a dike propagation, and the forecast might be, so we want to give actually more than one forecast, but the forecast might be that actually the dike stalls, or it might be that
dike actually propagates and leads to an eruption, right? So, and we'd like to assign probabilities to these various different scenarios. So the idea is that, you know, if you take data, you train this on data from lots of volcanoes, you might flag up things with individual volcanoes that may not immediately spring to mind from the past experience of those volcanoes. Okay, so this is kind of the idea. Unfortunately, we just don't have enough. Although we have lots of sentinel data, we don't have enough examples of actual time series of deformation. So lots of examples of individual interferograms of deformation, but the whole time series, you know, we're actually a little bit limited. So we're relying a lot then on simulated deformation maps. And actually, this is kind of the bulk of the work that we've been focusing on, is actually how do we simulate data well to try and be as realistic as possible. Okay, first of all, I'll talk about the work we've done on the real deformation maps. So as Juliet mentioned already, the LIXAR project, we actually processed a lot of data. Up to now, I think I've just looked a couple of days ago, and there's like almost 1.5 million interferograms that we processed around the world over straining areas and volcanoes. So most of these interferograms are over straining areas, of course, and there's an awful lot on volcanoes as well. We take these data, as Juliet also mentioned, and we process them in a time series manner. And sometimes that's tricky, right? So you get all kinds of problems with these data. So automating this process to process large amounts of data has been difficult. With some of the problems mentioned here that we've had. But nevertheless, we can eventually get out a product which gives a time series of information. So if you want to see more details on this, you can go and see Milan's poster, Milan Lizeski. Unfortunately, I took these numbers from the program, and it turns out when I looked yesterday that the numbers don't relate to the actual numbers that we posted. So just ignore all the numbers in this presentation. Okay, and just an example from the tectonic realm of the kind of product we can get out in the end when you process huge amounts of data. So this is the whole Tibetan region showing the east-west velocities from our data, combined with GNSS, I should say, in this case. And you can hear more about this from Tim Wright in his talk tomorrow. Okay, but back to volcanoes. So we already had this processing, this sort of standard processing, but we realized for the kind of time series we need a slightly, improved time series in a number of ways. So one is in terms of resolution. So we've gone from our kind of standard 100-meter resolution product, and we're now working at 30-meter resolution for volcanoes. That's one example. This is just one example of the time series we get out. And of course, it can be quite variable, right? Typically not linear. So in comparison to the strain rates and things, where things are a little bit easier. At volcanoes, we have to worry about more regular processes. The other issues, like lots of volcanoes have snow or vegetation on them and so on. So we've also worked hard to kind of pick out the best subset of interferograms to use. So by looking at doing a coherence analysis, it's just a coherence matrix for one volcano, the Hecla. So for this one, in fact, what we do is we just take the interferograms during the summer, the Northern Hemisphere summer, and make small base lines during the summer, but then longer ones from summer to summer. So it's obvious what you need to do, but there's some legwork to do this for every volcano. So Lin Chen already gave a talk about this, so there's many other improvements that she's worked on. And I think you can still go back in time and watch her talk. She gave it on Monday, but go to the Fringe site, you can still see that. Okay, so I've just got one slide on this. In fact, just with the data alone, we can already do some detection, of course. And this is something that Matt Gaddis has worked on. Unsupervised machine learning, we can just be applied to this in our time series directly. So we developed an algorithm. Essentially, what we want to do is flag up new deformation. So it's a little bit different to the aims of what Juliet was talking about. We just want to flag up when deformation rate changes or the pattern of deformation changes. And of course, this has to work when we have slow onset, and also has to work automatically. So in the next talk by Matt, you'll hear more about this then. But back to the deep learning. So yeah, that's the real deformation maps. So first of all, we're working with Sentinel data. That makes sense. Of course, we'd like to trawl through all the data archive, so look at all the other missions that we've had over time and still have now, and gather as many examples of these as we can. But nevertheless, we're still going to need these simulated data. So for our initial simulations, we've only used very simple sources. So what we do is we take simple deformation patterns like sills and dikes and so on, a few examples here, and we add some atmospheric phase screen that's correlated with topography. We also add some turbulent topography, turbulent APS. We mask some of this because typically we get bad coherence in some areas, and then we get a bunch of simulations like this. So we can generate as many examples of this as you want, of course, which is quite useful. This is another thing actually that Matt Gaddis has worked on, is using a so-called two-headed convolutional neural network for simultaneous location and classification of deformation. So again, it's a little bit different because it's well, in some sense it's the same, right? It's doing location of deformation, but also a little bit of classification as well. As Juliet talked about. So this is some examples of the results. I'll just focus on one here just to guide you through it. So what you're actually seeing here in the red is the results from the CNN, the network, and in black you're seeing the truth. So in terms of location, you can see it's approximately the same. So these are real data, by the way, so these were used for testing, not for training. And then also in red, you can see the sort of probability for the type of source. And also in black, you can see what an expert has judged to be the truth for each case. So generally speaking, this does a pretty good job in terms of categorizing into kind of simple dike versus sill versus no deformation type classification. Another thing we can do with these rather simple models is actually kind of automate the phase and mapping processing using a convolutional neural network as well. And so Eilish O'Grady has been working on this. Essentially, it works by taking the wrapped interferogram, feeding it into the CNN, and then actually what it does is calculate the ambiguity gradients. So the inter-ambiguity gradients, you probably can't see them very well, but they're in the x direction, the y direction on the right here. And then there's the further step then to sort of integrate these to get the actual unwrapped interferogram. So you integrate the ambiguity gradients first, and then you can just apply them to the wrapped data and get your unwrapped results. So I guess what works really well here is actually to do this in a probability-based way. So I think it's similar to what we would do. I've always been intrigued, right, because we can look at interferograms and judge really well when it's wrong. Do it by eye much better than any of our algorithms. So it's trying to simulate that. So when we find our own paths with our eye, sort of based on probability. So it's trying to simulate that. And it seems to be working quite well. So again, there's a post on this as well. You can go and catch up with Eilish tomorrow or later today. That's right. Come in. You've either got to go.
Next one round.
Come through. Okay. Okay, but coming back to this idea of forecasting, we can't rely on these sort of simple models. So this is the kind of model that I've talked about so far. This would be an example of a simple sill that's just inflating in an elastic half space. But of course, real volcanic systems are much more complex. Something like this with maybe liquid magma distributed through a magma rush system, stretching down to the full mantle, down to the mantle boundary. So how do we deal with this? One of the things we've done to start with is just trying to characterize by looking at all the examples we can of deformation, to try and characterize the kind of temporal evolution. So this is an example of 3 uplift episodes. And if you look at each of them, it turns out in all cases, you can actually, after some time, they become logarithmic in nature. So this seems to be a fairly ubiquitous process. So of course, this helps us to guide our simulations in the end. So this is trying to characterize the behavior of volcanoes by looking at all the data we can. Now, to explain this, the only method, the only process we've come up with so far that can explain this is some sort of flow through poroelastic medium and relaxation in a poroviscoelastic medium. So in this example here, if you look at the black line, that's just showing a logarithmic uplift, and the blue dots are showing the poroviscoelastic solution. In this case, it's just a liquid magma surrounded by a poroviscoelastic shell. So again, there's a poster on this as well by Camilla Neveu, so I encourage you to go and see that. Okay, so that's I think that it's fair to say that we from what we've looked at so far, we expect porous flow to be an important process, but actually we don't expect it to be as simple as that. So we're also working on more complex models which are trying to simulate better kind of magmatic systems we might have. So this is a sort of first go at that. This is using COMSOL, so it's a finite element model, and we're using the viscosity is based on the temperature, so it's a thermally dependent viscosity structure. Again, we have poroelastic magma mush zone, and then we're injecting magma from below. And then we're basically varying the range of the parameters. So there's lots of parameters in this model, so we've tried varying them within reasonable ranges, and these ranges come from all kinds of other fields as well, mostly from other fields, I should say, rather than from the field of deformation. So we can kind of characterize the range of deformation we can expect at the surface in these kinds of models. For this, I encourage you to go and see Rachel Bilson's poster tomorrow. Okay, and one other thing we can do is actually then try and modify these models to actually fit real data. So you heard about ASCIA both this morning and this afternoon already, so I don't really have to explain it, but it was subsiding for a long time, and then recently it's been uplifted. So we're modeling this in a we like to think a more realistic way, right? So going beyond elastic modeling that we've worked on already, and trying to include poroviscoelastic processes. Of course, a lot of these things are not very well constrained, but you can see Josefa's poster if you want to learn more about this. What time do I start? Okay, all right. Okay, so then we come to the actual deep learning training. So I have to say, up to now, we've really been focusing on these other aspects, and we really only just had started working on the forecasting. But I'll show you what we've got so far. So we've taken as training data just one example of propagating dikes. Of course, eventually we want to actually kind of simulate and forecast all the kind of processes you might expect of volcanoes. But we've started with propagating dikes. So we can simulate dikes, we can add some realistic looking atmosphere, as is done here. So you can see the dike up in the top left-hand corner, and it's gradually propagating in these 5 interferograms. And then we can use these to train a long short-term memory, an LSTM network. And essentially what we're trying to do is produce the last 3 of these interferograms, but only the deformation, and then forecast or predict the next 2. That's what's been shown here. So these are on the same timeline. So we don't worry about the first 2. We're trying to essentially filter the first 3, so to get the deformation out, and then predict the next 2. So these are just this is one. I'm going to show you one example of some preliminary results from this approach. So these were the data that were put in. So these are testing data now, not training data, of course. And this is the output. Right, so what you can see is a kind of filtered, not perfectly, but a kind of filtered version of these 3 interferograms looking at the deformation. But then the final 2, these are the prediction of what would happen next. And because these are simulated data, we know what happens next, and we simulate it ourselves, so we can compare that to the truth. So overall, these I think these are kind of reasonable preliminary results. This, I should say, this is really Matt's work. Rather informs me a transform approach is likely to do better, and of course this is it's an ongoing field of I guess of a lot of research in computer science, so we can take advantage of that. So eventually we'll need to expand this, our simulated data to include, first of all, be more realistic, but also include deformation processes all deformation processes of volcanoes. And by the way, that's not just magmatic processes, of course. You know, there are plenty of other processes that happen in volcanoes. And then one other thing that we're going to explore is the addition of physics to our neural networks. So this is physics-informed deep learning. The advantage of that, of course, is if you know something about the physics, you can constrain basically the range of possible model outputs, and in the end, you can use less training data as well. So I'll leave it there. I'll just put my summary up. Yeah, I'm happy to take any questions.
Who's got first question for Andy?
Yeah, thank you, Andy. I was wondering, so yeah, of course, you start with simple case of the dike propagation, and it's like something linear, or like the steps are like kind of easy to predict. I was wondering, in the case that your dike will stop to propagate or something more complex, like, do you think your machine learning will learn to or be able to predict that?
Yeah, so I mean, yes, it wasn't quite linear. There's some curvature in there, but yeah, you're right. It's a simple case. I mean, it depends on your training data. So if your training data include that, then it can learn that. And it gets back to this idea as well. In the end, we don't want just to predict necessarily one outcome. We can actually predict a range of outcomes. So in some, it might actually predict that it stalls. These are very simplistic simulations. Eventually, we can include simulations that really are based more on the physics. So you can, I mean, they're out there. If you look at Eleanor Rivalta's work, you can kind of predict where dikes will go and so on. So we can use those kind of simulations, and that will include stalling in some cases. So yeah, in principle, it should work.
I think Falk has a question.
For the dike, of course, if you have to wait the sentinel for 5 interferograms, you have to wait quite long. By then, the dike has erupted since long. So it looks to me that this could be really cool if you get ice eye, or if you go to daily images, then these kind of propagations or calculations have been done before humans can do it.
Yeah, that's a really good point. And yeah, I mean, we're working largely with sentinel data for obvious reasons, because we can. It's freely available. But actually, when it comes down to something actually happening in a volcano, of course, we can then take whatever data are made available, and it may well be ISI data with a one-day interval. So yeah, that's a good point. I mean, in principle, we don't have to wait for 5 images, right? This is just our first attempt. But I think some processes will probably want an even longer time series to try and figure. So if you had a long-term uplift, for instance, and you want to predict when something's going to happen, it might be months or even years later. So the time series you might need could be quite variable depending on the process. But that's something we need to consider as well, I think.
Right. Thank you, Andy. I think.
All right. Thank you.
Right. So. Great. Our next talk, you've already had a spoiler for, from Matt Gaddis. He's going to give you a bit more about the Lix alert algorithm.
So, hi everybody, I'm Matthew Gaddis, and I'm going to be talking about how you can use independent component analysis, or ICA, with time series of InSAR data to monitor volcanoes. And before I begin, I'd like to acknowledge my co-authors shown on the side of the slide, and also the funders of this work. And also a really quick acknowledgement of all the brilliant open source and free software that I use to do this work. So, why do we want to automate the detection of volcanic unrest with Sentinel-1 InSAR data? Here's a quick image of a LIXAR interferogram processed automatically for the Galapagos. You can see there's the relief shading of the DEM, some areas of incoherence, but at the bottom, at Sierra Negra, there's a really clear deformation signal. So even though these deformation signals can be quite obvious or apparent, the search for them in a huge amount of data can be really time-consuming and not possible for a human to do. So we could zoom out, and I show the Galapagos and the Eastern Pacific here. So volcanoes are red triangles, and the green are LIXAR stacks of interferograms. The darker ones mean we have a bigger stack. So looking even at just this small region, you can see that we have a huge number of volcanoes with a huge amount of data, and it all updates every 6, 12, 24 days. So it's just too tricky to look through. I'd also like to say that if volcano monitoring isn't your thing, the algorithms that we've developed, I think, really interrogate what's going on a volcano. So if you've got a stack time series for one of the volcanoes you're studying, then please, I hope that the algorithm we present would allow you the tool to do a sort of case study on that specific volcano. It's not just about monitoring lots of volcanoes. Previously, we've published a paper in 2018 where we had a prototype detection algorithm. We looked at independent component analysis at Sierra Negra. That's the independent component that captures the deformation, geocoded in Google Earth. And at the top, we show that we were able to track how this component was used through time. And then as the colors switched from, say, yellows, oranges to red, that's when we detected that the component was being used in a new or different way, basically being used more strongly. That's indicating from our algorithm that there's something unusual going on here, and this was about a year before the 2018 eruption. So flag it as a volcano you should look at in more detail. But we've got a new algorithm, and it's called LixAlert. We've gone for LixAlert because we started this when I was a PhD student, and I was funded by the Looking Inside the Continents from Space, or the LIX grant. And to do this, I'm going to have 4 changes that we brought through from our prototype. I'll talk about them today. One is increasing the variance of deformation signals so we can recover them. Secondly is a bit more carrying on from what Susie said about can we do ICA temporally now? And then I'm also going to introduce a few tools for visualizing lots and lots of volcano monitoring results using LixAlert and our results from applying it globally on the Jasmine computing service. So to start, we've had a quick look at some Campiflegrei data. Top left, I show a really shaded DEM, and top right is the output from the LixBAS processing. It's a pretty simple, clear deformation signal. We've got a few pixels of interest. On one of those, the orange pixel, located on the deforming region, we can plot a time series for. So from in terms of volcano monitoring, I'm not necessarily interested in looking at the deformation pattern so much, but what I am interested in is the change in rate of the deformation pattern. It does speed up and slow down. And when these signals do speed up or slow down, that's the kind of thing that indicates this is a volcano that's doing something different, and perhaps you should go and look at it. So to get independent component analysis to work at Campiflegrei, we had to change how we calculated our displacements. Instead of taking just the LixAlert standard, the LixAR standard short temporal baseline interferograms, we then found that actually we got better results when we maximized the deformation variance by calculating everything relative to a first acquisition. We did look at the rather time-consuming step of calculating all possible deformation between all possible acquisition pairs, but it didn't really improve things, and it did take a lot longer. So when we do apply independent component analysis to our new network, then we have independent components on the top, and to really see what those are, we tend to plot the correlations with the DEM on the second row, and how they're used to reconstruct interferograms of different temporal baseline in our training data. So how strongly was that component used when you want to reconstruct a 2, 4, or 600-day interferogram? So in the Campiflegrei case, you see one component which is not in any way correlated with the DEM, but it is correlated in time. You see other components that are correlated with the DEM, but not correlated in time. So we think one's deformation, one's topographically correlated atmosphere. We can then switch to our main LixAlert figure, which uses these independent components and then monitors the volcanoes using them. So on the left, we've got the independent components and also the DEM just to give it some georeferencing. We can take a baseline stage of 1 or 2 years. So that's both cumulative and incremental interferograms. And then we do a really simple inversion to reconstruct each interferogram using the independent components. So you could think of independent component analysis as a super efficient encoding. You could have a time series of hundreds or thousands of interferograms. But if it truly comes from just a few components, such as atmosphere or deformation, you should be able to condense the whole thing down to just a few independent components, and then you can then reconstruct any interferogram using combinations of those. So that's what we show in this simple inversion point by point. We also, at the bottom, plot the residual. How well can we reconstruct each interferogram? The idea being that we should be able to do that well if we're capturing all the processes that are in our interferograms. To see how these are used through time, we just fit simple linear trend lines and then plot how far points lie from that trend line. Warmer colors indicate a point that lies a long way from the trend line, and that's something that's perhaps unusual or unexpected. So I can run the monitoring for Campiflegrei. You can see the new interferograms come in, do our inversion, see how well it's fit. Back in the day, I would have shown the whole of this thing, but I'm going to jump ahead because we just have so much data now. It's so temporally rich, and you have all these time series, all these time steps. So on the top one, we had our deformation component, and in orange or warm or going through to red points, we flag when points lie a long way from these extrapolated lines of best fit. And that indicates that the component's being used in a new or different way that we didn't see in our baseline stage. So that's what we're hoping to do at Campi Flegrei, to identify when existing deformation changes in rate, speeds up or slows down. The topographically correlated atmospheric phase screen sees a really nice seasonal variation. It'd be much better fitting this with a sinusoid, and it's nice to check that that comes out in a result that we'd expect. You do see some false positives in the residual, some points that lie a long way from the lines of best fit. And when we look at those individual interferograms, we tend to see a really strong, unusual turbulent atmosphere in that interferogram. If you haven't seen a turbulent atmosphere like that before in the baseline stage, you can't fit it well. Therefore, you get a high residual. But we handle that by summing the residual per pixel and then averaging for each interferogram. So when you see an unusual turbulent atmosphere, when you are able to make the next interferogram, when that becomes the second acquisition in it, you tend to see a sort of sign flip of that. And therefore, when you're calculating residual per pixel, it disappears. So our algorithm does flag these with red, but then it goes back to cancelling them instead of them being prolonged periods of marked as red. So what about stratovolcanoes? That was the next thing. We know that when we move away to different volcanoes, we're going to have more challenging cases. And independent component analysis often works poorly here. And I think there's you could write a whole essay on this, but I think that one of the big issues are how non-Gaussian are your signals in time or space? Should you be applying it temporally or spatially? How independent are your signals in time or space? For instance, atmosphere and deformation are definitely independent, probably independent in time. Actually, we've had some talks that suggested that maybe atmosphere can have more of an impact on these things. But spatially, if you have a stratovolcano with a big topographically correlated atmospheric phase screen that's located on the cone, you could also have deformation located on the cone, so they're no longer independent. And the last point, I suppose, is a sort of computational one. We have really asymmetric data in terms of time or space within SAR. We might have tens or hundreds of thousands of pixels, but we might only have tens or hundreds of times. And that has a really big impact on the independent component analysis algorithms when you're iterating through in space or time, how many steps you get to iterate through and try and find your unmixing matrix. So a really quick synthetic example from an old paper. At the top, we have two sources. One is deformation, and one is topographically correlated atmosphere at Vesuvius, and they're offset by about 6 kilometers, which is shown on the vertical axis spatial separation. At the bottom, spatial separation drops to 0. Your deformation is located under the cone, the kind of challenging thing you could get. If you look at how spatial independent component analysis works, you get an expected result when they are spatially offset. It works well. But if you put the two on top of each other, breaking your assumption of statistical independence, then you get really poor performance. And this is where you think that maybe switching to temporal ICA could be better. So to do that, we took a time series processed with LixBAS at Vesuvius. From 2018, the big change is we just have so many more acquisitions. From having probably less than 100 acquisitions, we've now got nearly 300 in this time series. And that gives us computationally a much easier time when we're trying to estimate in time independence. So top left, got the DEM, top right is the cumulative interferogram for the whole 7-year span. You can see that at the top of the volcano, there's quite a lot of incoherence, but we put an orange pixel of interest just to the left in the figure, at least, of our maximum deformation, which you can see in blue. So that's about 15 centimeters of motion away from the satellite throughout the time period. And there are GPS receivers up there, so you can go and have a look and see how this compares with using that as ground truth, and they see the same substance signal. If I plot a time series of these points, the orange point, you can see you do have the subsidence, but stamped on top of it is something you better fit with a sinusoid. And this would really be challenging for us to monitor, because when you do see points starting to go upwards, has subsidence stopped and we've now got inflation? Is this a volcano that's doing something really unusual? Or perhaps you're just working at something that's a mixture of deformation plus atmosphere. So these are results from our independent component analysis, but now switched. So we're looking for temporal independence, not spatial independence. So these are components that are used temporally independently throughout the time series. You have one component that's not used very strong, doesn't correlate well with the DEM, but does correlate well in time. That's on the lower plot. Whilst you get another component which is very strongly correlated with the DEM and no correlation in time. What also makes me think, or us think, that that's topographically correlated atmosphere is if you look to the east on the right of the figure, you can see that you do get a lot of incoherence where there's hills there, but you do also see this component featuring quite strongly. So probably something to do with topographically correlated atmosphere again. If you look at the full LixAlert figure, then now our deformation pattern has a pretty much just linear trend. We don't see any of that seasonal or sinusoidal signal on top of it. The atmosphere, sorry, on the other hand, does still have some subtle sinusoid, and probably it's actually split between two components because it is a bit of a challenging one. So from a volcano monitoring point of view, this isn't super interesting because there's not really any unrest characterized at this volcano during this time. But it's nice to test our algorithm and show that we're not getting false positives. So after this, I didn't really know how to sum this up with a slide, but Richard Rigby took our codes, implemented them on Jasmine, and we go from running on 10 or 15 test volcanoes to about 1,000 volcanoes. And what makes this even more challenging is some volcanoes are in multiple Lixar frames, and then you've got ascending and descending look angles. So suddenly you get an email from Richard, he says, hey, all your jobs are finished. Here's a directory of 3,000 volcanoes, and each one has a figure per time step. And hidden in there are interesting results. So this is La Palma. On the left, we've got the independent components, and they're probably all just atmosphere, I think. They correlate really well with the DEM you can see. The kind of thing you'd probably expect when you stick a big lump of mountain in the northeast trades that you get blowing through the Canaries. But what is interesting is that when we saw the 2021 eruption, there were new deformation signals associated with that. Because we'd never seen them in our baseline stage, this was something that our algorithm flagged up with the red points and the last point with the high residual, because it's saying that this is doing something unusual, perhaps you should go and look at it. So how to visualize these thousands of results? There's interesting things buried in there. How can we do it? Well, we thought we could condense our time series, our Lix alert figure, into just two values per time. So a 2 by t, where t is the number of times matrix. We just have two values. One was for change in existing deformation, and one was for new deformation. But first, to do that, we'd have to take our independent components, work out which one was deformation. It's not always the top component that I pull out. That's the case at nice or interesting volcanoes, but not always the case. So something that we did to address this was we used a deep learning model that Andy has already introduced, which can classify or locate deformation. And traditionally, this is, we've applied it to interferograms, and this is, I think it's the same figure that Andy showed actually, or parts of it anyway, showing how you can use it to look at, say, on the left, a deformation pattern that was at Wolf, or in the center, something that's actually an atmospheric pattern, and at the right, something again that's a deformation pattern. So the deep learning model was great, saying which independent components are which. If we then go back to Sierra Negra, this is with our automatic processing on using the Lixbas time series on Jasmine and our Lixalert results, we can now say that IC0 is capturing most of the deformation. And I would just draw your attention, I suppose, to the vertical scale on the right-hand side of the axis. For this, it goes between 0, minus 0.5, and about minus 1. So while some of the other features do have nonlinear best fits through them, they're probably a lot smaller. So most of the deformation is captured in 1. And if we want to look how that changed, we can plot that on the X. And then if we look at our residual, which we think indicates if we've got new deformation we can't fit with our independent components, let's put that on the Y. So I can start monitoring, we click through in time, new interferograms come through. And in the case of Sierra Negra, I've already showed that when the deformation increases in rate, you start using one of the independent components differently. That means that the lines of best fit and the points have a large separation, many standard deviations, which we express in sigmas, and we start plotting in the bottom right corner of our plot. When the volcano erupts in 2018, you see some really interesting deformation, which we can't fit because we've never seen it before, and our algorithm now flags these points up in the top left-hand corner. Jumping to a different example, we could take Erteale. In this case, our baseline stage probably only has atmosphere in it. We don't think there's any deformation in these. So when you start monitoring, clicking through, ingesting new interferograms, recomputing your time series, when you do start to see deformation associated with the 2017 eruption, you can't fit this very well because you've never seen it before, you've only ever seen atmosphere. The residual spikes, that's in the bottom plot, you get warmer colors, and our points on the 2D plot start to go up the y-axis. Not quite as far as with Sierra Negra, but still enough for you to think this is something I should go and look at. So I've shown you a specific volcano for all times. If we want to keep our two-dimensional plots manageable, we could switch and take all volcanoes at one time, and then this could be an animated GIF, but it just gets too much going on with two new volcanoes moving all over the place. So anything that plots in the right-hand side or the upper side, or especially the upper right, is something that we think you should go and look at. And we take thousands of volcanoes, which is every single point, and condense this down to a few volcanoes that you, the volcano observatory user, anyone like that could go and look at in more detail. So for instance, here, the first thing I would go and look at for this week's summary is Tar. I'd probably go and look at some of the other ones too that are labeled, but the points down in the bottom left, hopefully if our algorithm is working well, these are volcanoes that aren't doing anything unusual at the moment. Sadly, what we're finding is that if you do go and look at some of these time series, you tend to see that actually errors in our LixBass processing get picked up really well by the algorithm. So it's a mixture of the challenges of automating LixBass on a big scale. So what next? I think we'd like to improve the quality of our LixBass time series. I think one of the best ways we could do that is collaborating with the Comet Volcanic and Magmatic Deformation Portal. They've got really great LixBass time series. We're working on LixBass time series. If we work together, we could use some of their brilliantly quality controlled data, which we don't really have at the moment. We're also looking at a web-based interactive LixAlert figure. This is in beta at the moment, and then at some point, hopefully we'll deploy it on the web, maybe on the Comet Volcano portal. So if you've got a volcano you're interested, you can go and see our figure for each time step, or you can look at the overview figure and say, are there any volcanoes that are doing something unusual at the moment that I'd like to go and look at either on LixAlert or use my own data in more detail. Also, we absolutely love it when somebody uses the code on a volcano that they're doing a case study on. You probably know a lot more about that volcano. You definitely know a lot more about that volcano than I do. And we always learn things about how our algorithm is working or not working. So all the code is on GitHub. And if anyone wants to use it, I'm always happy to answer questions or raise an issue on GitHub. So thanks very much. I'll leave my conclusions on the last slide and I welcome any questions.
Thank you. So you're starting with what? With geocoded, unwrapped interferograms?
Yep, geocoded, unwrapped interferograms.
And filtered or not filtered?
Filtered as part of the standard processing by Lixar. That's Goldstein filter.
Okay. Okay, so, and could you do some of this stuff also with wrapped interferograms?
I've never tried. I don't know if anyone has used independent component analysis with wrapped data. It'd be interesting to know how the fringe is shifting might bring the independent components being different for every single position the fringes are, but it's not something I've tried, but it would be interesting.
Yeah, everybody talks about unwrap errors. We know more or less what we are looking for. So if we can start with wrapped interferograms, maybe that's better.
I think one of the things that I really struggle with deep learning is remapping your data into the kind of value range that you can use with deep learning. So deep learning wants your inputs or outputs in the range 0 to 1 or maybe -1 to 1. And that's because of the activation functions and how they work. When you start working with unwrapped data, that's so challenging because we have an open-ended set of maximum deformation values, and it can be really hard to work out how you rescale things with big signals or small signals into this interval. But what I think would be great about wrapped data is you know what your interval is, it's always the same, and you are condensing into that same range. So I do think there's a lot of merit to working with wrapped data in the future, especially with deep learning.
Any other questions for Matt?
Not, can I ask, and the resolution influence a bit the result? Because Andy was saying 30 meter is better than 100, so.
The big impact is it's definitely more computationally difficult. It's much more computationally difficult to do fast ICA, which is part of the ICA package we have. It's not something we've tested at the moment, but I think it probably will improve things. It probably will improve things. In the simplest sense, when you're working spatially, more pixels means more steps to iterate over your data in much the same way that I said more temporal richness is really useful. So more pixels in that respect gives you more chances to update your mixing matrix, and that should be really useful for the algorithm.
Other question?
Okay,
thank you.
Thank you.
So we can move to the last one. New Rotterdam, Clara. Was correct. So we will move to Canada.
Yeah.
Hi, everyone. My name's Drew Rotherham. I'm an Earth observation scientist at the Geological Survey of Canada. And I'm going to be talking about the volcanic risk reduction program in Canada and our progress towards an operational INSAR monitoring system for the Canadian volcanic hazard. It's really humbling, actually, hearing all the presentations and seeing everything that's been done with Sentinel and LIXAR, because I feel like we're definitely playing catch up. We've only kind of really recognized how threatening the Canadian volcanic hazard is recently, and we spent the last couple of years trying to develop an INSAR system based on RCM. So volcanism in Canada, yeah, when you talk about Canada, most people don't really think about volcanism. You think about snow and hockey, but there does exist a non-zero volcanic hazard. So essentially, it's mostly on the Pacific margins. So we've got the chain of volcanoes that continues up the Cascadia subduction zone, and it goes through Oregon, it goes through Washington State, and there's no reason that it stops at the border. It actually continues right up through British Columbia, through the Yukon, and right up into the Aleutians in Alaska. So here's kind of a map on the left showing most of the volcanic cones that are known. And here's an example on the right of an air photo from a trusty Cessna 172, showing kind of what the volcanoes in Canada tend to look like. And I think part of the reason they've been commonly underestimated for so long is, well, there's a number of reasons. But I think a major one is our volcanoes don't typically look like your typical menacing stratovolcano. They're mostly glaciated, so if they erupted prior to the last glacial maximum, they've been heavily eroded. There was a lot of eruption during deglaciation, and there's some eruptions during glaciation, and so they've got really atypical structures. The other, main reasons they've been commonly underestimated is there's been no monitoring. So if you don't see any volcanic activity, you don't really think about it. And there hasn't been any volcanic eruptions in Canada in living memory. So in the 90s, when a lot of these volcanic cones were mapped, there's 348 known vents in the Pleistocene age or younger, and 54, that's a minimum bound, 54 are known to be active during the Holocene. So a couple of notable events. 200 years ago, there was approximately 200 years ago, there was an eruption at CX Cone, which is right around here. And a little over 2,000 years ago, there was a major Plinian eruption at Mount Meeker, and that was the ejecta from that eruption have been found as far east as the other side of the Rocky Mountains, which is like over here. So it was a pretty major Plinian eruption. Another notable event was a 2007, 2008 seismic swarm at Nazca Cone. And I did say that there hasn't been any monitoring, like there hasn't been any systematic monitoring, and that was actually found kind of fortuitously. There was an exploration group doing seismic, and they just sort of noticed that it's a seismic swarm. And then the emergency seismic team kind of mobilized and monitored that event. So at any rate, based on past eruptions and evidence that's there, the annual probability has been estimated at 1 in 200 for any eruption, and 1 in a little over 3,000 for a major eruption, which is kind of on a similar scale as a Cascadia megathrust earthquake. So in 2021, the GSC published an open file where those events that I talked about previously were lumped into 28 distinct volcanic fields and complexes. And a threat score was assigned to all of these using the USGS methodology for the National Volcano Early Warning System. So they use the exact same methodology to assign threat scores, and which may have been surprising to some, but a bunch of the local volcanoes, so here's Vancouver, where I live, right here, A bunch of the very local volcanoes ended up having high or very high threat scores. And so some of the things that drive these threat scores are obviously proximity to infrastructure and population centers. And another thing that drives them is obviously recent eruptions or current evidence of unrest. So I think it was in 2013 or so, there was fumaroles that were noted to start off-gassing at Mount Meeker. And Mount Garibaldi has had several eruptions that are maybe around 10,000 years old, but it's so close to population centers that it really drives up the threat score. Mount Cayley itself has a number of hot springs that are not monitored at the moment either. So with that threat ranking, you can see here, this is kind of the portfolio of Canadian volcanoes. We've got two really close to population centers that rank in the very high threat range, a whole bunch that are close to, or some a little bit further away from population centers that rank high, and then a few in moderate and low. And here's kind of how they stack up compared to American volcanoes. So we've got Meeker and Garibaldi using the exact same methodology, kind of right up there with Mount Baker and above Yellowstone, certainly. So, like I said, up until about last year, Canada had no real dedicated volcano monitoring system in place. We didn't have seismic stations or routine gas monitoring or any of the bells and whistles. And the U.S. recommendation from that NBUS report that I was talking about before recommends minimally a remote sensing approach for volcanoes that rank low and above. So, of course, we would like to put all the instrumentation in the world, the GNSS and seismic stations over our very high threat volcanoes. But since we're kind of starting at square one, we decided to go first with the remote sensing approach, where we could just at least cover and have some form of routine monitoring, and then use that remote sensing approach to, if we did start to see some unrest, to justify the added expense and complexity of instrumenting these volcanoes. So here's what we set out to build early on, really quick. So we wanted to make an fully automated volcano INSAR monitoring system. So starting with CSA infrastructure, which is RadarSat constellation mission satellites in orbit, they get all those imagery obviously get downloaded and stored in a persistent storage. We access it via the CCMEO API, and this is kind of what we want to start building. So, an automated processing system, persistent storage, and a front-end UI. And yeah, so we don't want to exclusively use RadarSat constellation mission, but it is a source of secure and domestic data that we can rely on, and we know it's going to be acquired routinely and at high resolution. And so this is kind of the backbone, this is the workhorse of our data flow. It's a constellation of 3 identical satellites, and a lot of the talks, I don't know if many people know about RCM that much, but a lot of the talks have really been about Sentinel, and maybe I've seen some RadarSat 2 data at this conference, but I don't think I've seen any RadarSat constellation mission data, which is kind of disappointing, really, and I think is a huge gap in potential. So this is the 3rd generation of SAR programs, RadarSat 1 and RadarSat 2, and RadarSat 2 was used a little bit more and more for INSAR, but largely these were used by D&D and Canadian Ice Service and users like those. So it was launched in June 2019, so we don't have those super deep stacks of data yet, but they're on their way. We're slowly acquiring. It's C-band radar, a lot like Sentinel, but the difference between RCM and Sentinel is we tend to collect over our volcanic hazards at 3 to 5 meter strip map mode. So we typically use 3 meter if we can. If the footprint's not big enough for 3 meters, then we'll switch to 5 meters, or maybe we'll use a couple frames of 3 meters. But what the really big difference is, especially from RadarSat 2, which had a 24-day repeat, is we collect data at 4 or up to 12 days repeat pass. So in kind of low priority periods, we collect at 12, but sometimes we're often enough, we're actually able to collect 4-day repeat, which has a number of implications, especially for INSAR with fringes and coherence. So when we set out, these are the guiding scientific and development principles. We wanted to align as closely as possible with the open science and open government policies as defined by the Treasury Board of Canada. So typically, as government scientists, we're supposed to do everything out in the open and make as much as we can open source, which has been made really difficult by the protected nature of RCM data. And of course, it's a little bit different with Sentinel, where Sentinel is free and open source and open access. RCM is still kept a little bit under lock and key, which is unfortunate, but it's just the way things are. We want to make everything cloud native, but portable. So we ended up building a lot of things with containers. So everything right now runs on AWS, but there's no reason it couldn't be ported over to a physical server or to Google Cloud or Azure. And from the outset, even though we wanted to rely heavily on RCM, we decided to still make it sensor agnostic. So we've built in the flexibility to process RadarSat-2 and TerraSAR-X. Processing Sentinel-1 seems a little bit redundant at this point, but we've still got the capability to do so. And we relied on iterative development principles. So we started with kind of a minimal viable product. We raced to that within a few months. We got that going. And then we've kind of been building out the bells and whistles as we go. So here's a basic cloud architecture. I'm not going to dwell on this too long, but essentially we have a fully automated process where we check for new imagery daily, and that kicks off a simple queue service that tasks a job. We've got a persistent storage, and that automatically spins up the compute resources we need. We crunch through all the interferograms, we process them, we destroy the compute resources, we store everything in persistent storage, and then we serve it to our own dashboard using WMS services. So this looks very cloud native and it looks not portable, but there's no reason that any of these functions couldn't be simply, almost every component that we use in AWS has got an analog in a different cloud provider or something that we could use on-prem. So here's kind of in the first year, our first attempt at a dashboard. So we've got kind of a situation, a national overview of everything we see in the volcano portfolio of Canadian volcanoes. And so we've got listed the most recent SAR image. So this is, I took a screenshot just before I left on Saturday. We just sort of maintain a volcano status of if we've observed any unrest or not. So, we're just sort of doing things a little bit manually at this point, but as we mature and get deeper stacks, we want to get a little bit more complex. And seeing all the great work by previous presenters has given us a lot of inspiration moving forward. So yeah, we've got a kind of an overview page and a detail page for each volcano. This is kind of what our analysis platform looks like. So we've got a coherence matrix on the left, and I see a lot of these kind of as diagonals, but we decided to flip it 45 degrees. So instead of date, we've got temporal baseline versus primary image date. And we've got different GUI components for baselines and things like that. So we can kind of go through here and manually kind of inspect, which is still feasible at this point because we've got so few images and so few sites, but as we scale up, it's going to become less and less feasible. We're getting better at atmospheric modeling correction, but it's still a bit of a pain point for us, as it seems like it is for others as well, so that's comforting. So that's essentially where we're at after 1 year of development, and maybe I'll just go into some examples of what we've observed over the first year of running the system. So somebody told me more than once, if you start looking at INSAR stuff, you'll start seeing stuff, and we did. And so here's some interesting, I've just got a few interesting observations. So we've seen really massive slope deformation of Mount Meeker. So in 2010 was one of the largest landslides in Canadian history. It happened on the other side of Mount Meeker. And last summer, we kind of noticed that, and this was when we first started running the system, right away we started noticing these deformation anomalies. And so this slope, which usually moves at maybe 2 or 3 centimeters a year, started really accelerating. And it happened to be a really hot summer. So it was, the hypothesis is that, there's either glacial melt that's driving and making changes to the groundwater regime, or perhaps even frozen ice underneath that's holding the slope together. But as we get warmer and warmer climates, these are going to become more and more of a problem. So even for RCM, at 12-day repeat at 3 meters, this was moving so fast that we couldn't even wrap it by the end of July. Fortunately, it started decelerating as the temperatures cooled, and it didn't lead to a catastrophic failure, but yeah. Other interesting observations, we started noticing a lot of subsidence of lava tubes at Mount Edsiza. So these flows are, I think, 1,000 or so years old. They're not very vegetated, which means they've got kind of fabulous coherence, throughout the year. And we started noticing kind of these sinewy patterns, and we shopped it out to all the geologists at the GSC and kind of crowdsourced an opinion what they might be, and the consensus seemed to be collapsing lava tubes. Kind of interesting, but not really a volcanic hazard unless you're trying to build a pipeline or something across it. But one thing we did observe in the first year was magmatic unrest at Mount Edgecumbe. Now, we weren't the first people to see this, of course, but we were able to collect INSAR measurements over the winter period. So that's one thing about RCM is the 4-day repeat. So here's a 4-day pair from January 5th to January 9th. And it's usually a time of year where you expect pretty garbage coherence. But with such a short time between acquisitions, the temporal decorrelation doesn't really have enough time to take effect. We haven't got a deep time series of RCM data over Edgecumbe yet, but we were able to take a look at some of the RadarSat-2 spotlight data over the same site, and we've got ascending and descending spotlight, and these are both approximately 1-year pairs, but we did process the full network, unfortunately at a 24-day repeat. And we did notice quite a bit of both uplift and subsidence in the line of sight on the ascending, and a lot of subsidence on the descending. So since we had ascending and descending, we did a quick 2D decomposition, and we noticed that, as you might expect, a lot of horizontal movement kind of on the flanks and a little bit of vertical movement near the center of the edifice. This was originally in a paper by, I think, Grapen and al., and they noticed about 8 centimeters of deformation per year. The time series was very linear, and one thing we noticed was we weren't seeing quite that much, but we were getting a lot more variation in our time series, so we were getting a lot more changes in rate. The other thing is, since we've got spotlight data and the footprints are so small, almost certainly our reference pixel is probably, or a reference zone, it's reference region, is probably within the movement zone. So I would expect that we're definitely underestimating this deformation. But we're not too concerned with time series yet, because we're just trying to get a fringe detector at this point over all volcanoes. So that's kind of where we're at currently. So we're running fully automated. We're generating new INSAR measurements daily. We've got some deformation phenomena observed in the first year, but we still have a lot of work remaining with better atmospheric corrections, automated detection, and we'd like to really scale up our deformation time test cases. So our plans for the future are to grow a trained data set of natural fringes, and also grow the number of volcano sites that we monitor globally. So if anybody has any interesting sites, I would love to hear about them. Please get in touch. Yeah. And yeah, so I'd just like to give some acknowledgements to some of the folks at the GSC, Canadian Hazardous Information Service, DRDC, the Canadian Space Agency, and CCMEO.
Thank you, Drew. We've got time for questions. Marco? Pass the parcel.
Is it working? Okay. So I'm your counterpart a few miles down the road in the outer Vancouver, as of 3 months ago at the Volcano Observatory there. And we would love to have RCM data for our volcanoes as well.
When you say Vancouver, do you mean Vancouver?
Washington.
Washington, okay, good. All right.
Have you gotten any good results in terms of coherence on the volcanoes in Canada that are more likely to the ones that we have?
Yeah, surprisingly, we didn't think that we would have great results over the winter. Fortunately for us, the winter is a less busy time. So the RCM constellation is fully tasked right now over Canada. The rest of the world, it's undertasked, and there's a capacity for other sites. But over Canada, it's fully tasked, especially in the spring, summer, and fall. Over the winter, it's generally not fully tasked at all, and that's when we're able to get really dense 4-day time series. We get bumped sometimes outside of the winter. And so with that 4-day time series, maybe we're bouncing off of snow. I can't say for sure, but we're still able to maintain coherence with those really short temporal baselines. So yeah, we do get pretty decent data in the winter.
Good to know.
I think Andy has his hand up.
Yeah, thanks. That was really interesting. I mean, I guess the reason a lot of us, or at least I, haven't really looked at RCM data is because of where the data are mostly acquired. So I didn't know it was an option to actually. Is it an option for us to request data elsewhere, or?
Well, you'd need a partner within the federal government.
Right.
So RCM's fully dedicated to Canadian scientific purposes. Scientists within the federal government do have the capability to task. External partners don't, but if you have a partner within the federal government, yeah, it's totally, you won't get the same priority as some of the more stakeholder users, but it is possible to put in background taskings for sure.
Okay, but is a federal employee of Canada likely to kind of want to look at a volcano somewhere else outside of Canada?
If there's a scientifically justifiable case, such as observing deformation that may be in the same style as Canadian volcanoes, so that we can learn more, then yeah, I think there could be a scientific case. Yeah.
Other questions?
Okay, let's close that session there then. I think there's some good material, particularly in this last talk, which will be relevant to the roundtable, which it's not scheduled to start until 10 to 6, so we should probably keep the time in case other people want to join us, but please stick about and contribute to that. And if anyone wants to chip in on what the seed question should be for that discussion, come and talk to us in the break now as well. Thank you.
Thank you.
Yeah, okay, Paul's suggesting a 5-minute break, and then please, everybody come back. Yeah. Yeah. Well, so we have a slide, I guess, to show it together now. How can I get something on track? Is that a laptop or is it the PC? So I could just put in a memory stick. Yeah. Okay. Sorry?
So basically, that's all I've got. Yeah.
Yeah,
Do you think
so-
we want anything else?
Yeah.
This is the thing that ESA provide.
So I think, yeah, mission about volcanoes, yeah, that's kind of the new one, and complementary. I was thinking about like benchmarking, you know, like, you know, wondering like if we are in a.
So we'll keep the rest of that hanging out somewhere outside.
Yeah, please. I mean, or come and do the talking. That's true. Yeah. I mean, I thought I would just kind of stand and hover and type things anyway.
That sounds good.
Yeah.
The typing thing.
Yeah. Well, I already volunteered Fabian for doing the reporting
I'm
back, so
gonna
I
do
feel like
the
the least I
report.
can do is the typing.
Oh, excellent.
Right, so you're good. You're good. So yeah, I will be here, and that's yeah. So I was wondering if,
Something about benchmarking.
yeah. So the benchmarking, there is, I mean, different level of benchmarking, right? It could be. I mean, we have been talking about that, comparing like processing chain. About there is the insert processing, but now there is also like, you know, many groups and many different people are developing anomaly detection and.
So I could say, do we need benchmarking for performance?
So, yeah,
I mean, processing, time series analysis,
Yeah.
machine learning.
Yeah, exactly. Just have, you know, when you want to compare your performance when you're developing something to things that already exist. Having
good idea. Time series, machine learning applications. Okay. Oop, I can't spell or type. Formatting.
Yeah, also, and the harmony, probably people will also, yeah.
They will have
put
some input.
Some input on harmony or just some thought about harmony.
So shall let's just move this onto the computer and put that up on the screen then. Fringe 2023.
The other thing is everybody, in other rooms that are so not that interesting.
It's not confidential.
How is the channel getting so much spam?
Yeah. All right, it should be coming up now then.
just trying to get them onto this computer, which proves hard. I added a little bit where I put them. I mean, they're not, no, not that. Yeah.
Okay. On that computer. Yeah, I don't know.
But that's fine, I added something about DRR.
Yeah, I just thought it was important. I don't really care how we phrase it. I think, yeah, well, you've all done this a lot. Yeah. Paul? You've got the slide up.
I know, okay.
You're trying to live anything.
I will try and type, not so everyone can see my typing, because I'll inhibit my typing, but,
Just know that, yeah, this is the screen that's being shown up there.
okay. So if you,
Yeah, I don't want me to type and you can talk.
I don't mind, I mean, you're volunteering to type.
Volunteering to type.
Oh, brilliant, okay, yeah.
I think so, yeah. Yeah, I think they want to be like live edit. Yeah, like write it down, people see. I volunteered to type. Okay. 2 season charge, I volunteered to type.
Okay. Okay. I will report on Friday.
Yes, so, yeah, on Friday, is it supposed to be 2 slides for all of volcanoes, or 2 slides for volcanoes 1, 2 slides for volcanoes 2, 2 slides for volcanoes 3?
Previously, it's always been 2 slides for volcanoes.
Okay, all that's
Yeah.
good.
It will be, yeah.
Okay.
I think I did this one year.
Okay. And you're gonna do it?
Yeah, I mean, I can, I can report it.
Yeah.
And we.
For all 3 sessions, or do you want us to feed it? Do it for all of it, that's great.
I think
We'll check in.
Yeah, okay, great. Yeah, okay.
better, I can send over the 2 slides like before
Yeah.
Friday
Yeah.
for the
Yeah.
chair. Then if you have input,
Right, should we do this? Or if you're early,
If I can text that. And we can hand around the microphone, I guess.
yeah. Make sure you start probably right.
I thought it was late. There's a queue for the news. Oh, there's 2.
Yeah, there's a problem with this building, actually. There are someone each floor, and they're just come in the basement.
None of us know where to look, so.
Then they're also not obvious. Like one. Yeah, it's a stupid building. Yeah, it's like heritage property.
It's not whatever the kind of.
Not that I've heard. I kind of imagine from my life. You never know.
It's not university.
It's very like on brand.
it was good to see the ongoing picture, like
Yeah.
the picture. And,
Yeah, we have to make it work. Yes. Yeah, it's going to be like a great maternity one. There's all these old things that are really mature now, and really well developed, and then a whole bunch of new things. And normally there's not such a clear like line. Normally you have new things coming on as you finish up the old ones. But maternity is really really clear split.
Yeah.
Yeah, and I think you should chat to the posters.
yeah. So I was a bit on my poster on Tuesday, but I want to look at
Or I think
Disaster risk reduction. Not inside, probably topography.
Go down.
Okay, show me this on top.
Can you, your keyboard doesn't work, period?
Yep. The mouse works, I can move my mouse when I try it.
That's not how it's protected view. Because they know something else. Maybe that's it. Okay, yeah, just because it was downloaded to the email.
Just so you're aware, the doors of the Roger Stevens building, like the traffic center stops working at like, I guess, 5:30 or something.
Okay.
Basically, if people don't get in, they can't because the doors don't open anymore.
Okay.
We have to wait for like a cleaner to come by.
I don't think it's a keyboard.
Okay.
So, just so you know.
Protected view
Okay.
on the
Not actually getting it tonight, but not already.
They should, you know how they have the people that guide us
This is like
where to
a
walk?
Fringe
That's one
account.
of those, just the-
Exactly, yeah, yeah.
Okay, fine.
This is the black.
Okay, great.
Yes, that's fine. Thank you. Okay.
Apparently the building closed at 5:30, so people wanted to rejoin this late, they can't get in the building.
All right, so, okay. All right. Should we send them?
I can make it
I don't
fill
think
out.
it's usually,
But I
that's
can't make
what
it
it is.
work in the screen.
Can you continue just to check?
We can also have this too. Could someone do us a favor? Apparently this building was locked at 5:30, so if anyone wanted to come in late to join this discussion, they'll be stuck outside the door. Do you think one of the Leeds PhDs could run down and just check? And if there's anyone accumulating there, let them in. Thank you. I guess it'll just be the one by the Fringe banner. Don't spend ages, Rachel, just if there are people there waiting. Thank you. All right, shall we start? Okay, let's kick off this the roundtable discussion for the volcano section. So the aim of this session is to have a discussion around the important issues, particularly things that we might want to communicate to ESA. And it's an opportunity to pass on recommendations to ESA from the community. So we've got a couple of seed questions to get us started. But if you have anything you'd like to add, please jump in and we'll try and record it. Juliet offered to capture the discussions and do the typing, and Fabian was going to report back on Friday. So I will start off with the first question, which is the same as it is most years, I think. How can these missions be optimized for volcanoes, meaning the current ESA missions and the future planned ones that we heard about on Monday? And we've added a statement asking about complementarities with other missions, like ALOS, SAOCOM, maybe RCM as well, if we can get the data. Does anyone have anything they'd like to start off with? Andy, thank you. Mike? Thanks.
Thanks. Yeah, I'm just going to start off with the obvious one, which is that for Roselle and Central Next Generation, it would be great to have two looks acquisitions so we can get north-south motion as well. So I mean, I think every session should recommend that. Let's try.
Yeah, and you can probably add that as a kind of fundamental thing. We appreciate continuity in time series, and that's all still great, and we still want it.
But Andy, what are you implying they should go from, have both right and left looking? How are you going to get the north-south with, just by adding more satellites?
It's like what we have with Sentinel-1 in the burst overlap regions.
Oh, yeah,
but,
yeah.
But over the whole strip, so two looks everywhere, so just essentially increase the overlap. And it's feasible, but yeah, as was mentioned on Monday, or was it Tuesday, there's a downside, right, for other applications, but for us it'd be ideal.
So is your recommendation for Sentinel or for future missions? Only for future missions, right?
Future missions, yeah. So, but I guess it's feasible potentially with Sentinel or Next Generation as well.
Mm-hmm.
I would say I would add a more mundane request. I heard something over lunch or earlier about that there's a question about whether Sentinel-1A, C, and D would not be doing both ascending and descending each satellite. I think somebody.
Yeah, so I was saying that. So it's more a case of how they divide ascending and descending, which is a problem for Harmony, but not a problem for Sentinel-1.
Oh, okay, so you'd still have both giving, okay, just for
It
Harmony,
just
sorry.
depends which Sentinel they assign which ones to, because Harmony will only be on one of those.
Got it.
Yeah, so I don't think that's too much of a problem for Sentinel, but it's certainly a problem for Harmony.
Okay.
Thought of another one too. So there is this plan to park Sentinel-1A once 1C and 1D are up.
Okay.
And it'd actually be quite nice to have that acquiring data as well, if possible.
Yep.
Right,
Good idea.
Yes, don't turn it off. If it ain't broke, don't fix it.
So I think we should make clear at the roundtable that the potential, I mean, we came to here to meet today in this session, the potential what INSAR or what we with our community, volcano INSAR community really have. So, As I said earlier, if we get daily images or half daily or hourly images, what eventually is going to happen, then the people at the volcano observatory in the Hawaii Volcano Observatory who are freaking out when there's a dike propagating, they have to try to image it as good as possible. And these algorithms which our community can develop, it can really solve the problem. So okay, that's the first thing what we should make clear. And then what we need is really good data sets. Sentinel and to develop these algorithms, multi-satellite data sets. So we need a few, well, somehow funny that I'm starting again with supersites, but we need a few volcano supersites where which should be driven a little bit differently than what we currently have, or the current geohazard supersites. They are driven by the volcano observatories, and okay, it just goes according to the needs of the volcano observatories, and they have to make sure that they get the data what they need. But what we need is really a few supersites where we get really as much as possible ice-eye, what is it called, capilla space. And I don't know how many data you can get with Cosmos Skymet now, but we should just shoot for one, getting full data sets for a couple of volcanoes really as good as possible, so that our community is ready when all these things like Rose L and Harmony are online. Otherwise, these satellites are there, and we are just starting to develop algorithms. Well, you guys are doing it here, but many people will start developing the algorithm just by the time these things are launched. And then by the time the algorithms work, they're gone. So we should avoid that. If we get good data set right now, we can be ready by the time all these satellites are launched.
So are you talking about using current missions without open data policies as kind of an analog for developing things for nice RC? Or just saying that we really need all data everywhere?
We need, as much as possible. Yes. Well, no, not everywhere. For a few sites.
Okay, well, so I guess, but the context of the super sites was always that these are sites where there was a demand for the data scientifically. There was a scientific case to be made for having it, as well as a hazard case. And then there are the other programs like the CEOS Working from Disasters volcano programs, which are actually more kind of focused on providing it to volcano observatories. Are you proposing something different again to that?
Yes. Data sets to learn machine learning algorithms, to apply machine learning algorithms.
Okay.
One thing we're learning from developing machine learning algorithms is you need data from as many volcanoes as possible because they all behave differently. So focusing everything on a few super sites doesn't actually fill that need. So we're kind of back to all data everywhere all the time.
I mean, that'd be great. One thing that
I
Fox
think we are
mentioned.
not,
Sorry, go ahead.
not many people, everybody is just using what we saw here, it's just Sentinel. But nobody is really combining all these different sensors, and that's what we're going to have in a couple of years. NISAR, Sentinel, whatever, ALOS, we don't do it. This machine learning or those things what you guys are doing, if you were using multiple satellites, it would get much better.
Yeah, I think absolutely. And the other thing that, is a constellation approach is also important in terms of latency and being able to detect changes that happen rapidly. And there's also a coordination question there. But I was going to add something to what Falk said before about commercial missions, ISI and Capella Space. And it would be great to have a pathway for commercial operators to provide data for hazards, which I think is not really there at the moment, although there's some kind of ad hoc relationships. I don't know if that's really a recommendation to ESA, but...
I think ESA have a lot of weight in things like CR, so it's a good thing.
Yeah.
Always a good thing.
Yeah, and they run third-party mission things with limited amounts.
With the current geohazard super sites, okay, the volcano observatories, they are happy and overwhelmed with the data they have. And we don't get all the data which is possible. And okay, that is because it is hazard driven and driven by the needs of the volcano observatories.
Yeah, and I think the other factor there is also the acquisition strategies behind the different missions, because of course, Cosmos SkyMed has the background mission for volcanic hazard, but TerraSAR-X, for example, doesn't.
Doesn't exist typically, or it's not optimal.
It's ad hoc.
And I mean, the other thing with, ALOS or ALOS 4, when it comes out, it's still going to have this very heterogeneous acquisition strategy. So I wonder, for sure it can be very valuable data for particular situations, but I wonder how, I guess maybe a service, something like LIX could handle a very heterogeneous influx of data, but it seems a lot of these systems are really designed for very regular acquisitions. So I don't know. When you're going down the machine learning track, I wonder how having a very heterogeneous set of satellites and types of data, how easy that is to implement.
But for me, it is the computer who is going to do it. Shouldn't be a big difference to, if it works for one satellite, you can do it with another one. And then you combine those different things. And that is then
We couldn't have done this with NVSAT. So a lot of what we're doing relies on the reliability and the continuity of the data sets you get with Sentinel-1.
Yes, but we could get with Cosmos SkyMed as well, or we do have, but not as good as it could be.
I think Cosmos SkyMed is the only other one we could probably do that with.
And I would imagine
RCM.
NISAR would be a good addition.
RCM would be good.
Yeah.
Because it will be very similar in terms of 12.
Yeah, so NISAR I think would work. But I should say, in terms of our deep learning, the CNN that I showed that's operational, it's basically a fringe detector. We haven't really tried it, but I would imagine you could just feed any PNG file into it, and it would be just.
Yeah, I was actually going to put it here, but in the case if the problem really is the transferability of the model we developed training for Sentinel-1 to some other satellite, whatever difference that I have. Things like transfer learning, which your school was already doing, to build this thing, could very easily bridge that gap. You could have something that's primarily trained on Sentinel-1, and then you use transfer learning techniques with a little bit of extra training on radar sound, Cosmos SkyMed, or whatever. I'm pretty sure you will get into that. We got you there from detecting Dodger scans to detecting printed programs. I'm sure we can do it from Sentinel-1 printers to radar sound, Cosmos SkyMed, so it's not a huge problem, I think. Something that can be handled.
Should we move on to the next two questions? Does anyone have anything else they want to?
Oh,
Oh, brilliant. Okay. Yeah. Do you want to have the microphone?
I don't know if it has been discussed before, but it would be a very particular recommendation to ESA regarding Etna volcano, because the ascending track doesn't have the proper cover over the entire edifice. But we have the border of the images just on the top of the volcano. And it's very particular, a very, very particular recommendation, but I don't know if for ESA it will work, perhaps.
But this is the swath boundary you're talking about? They can't do anything with that.
Yeah, but okay, I just said.
If you're on the burst overlap region, that's usually a good thing, because you get twice as much data from different angles.
Yeah, that's right. Yeah. But there are some issues also that we have with two different.
Does anyone have any? Oh,
Yeah. I don't know how to put that, but maybe Fabien can help me. But we should not forget about small-scale volcanoes. I'm thinking of Guadeloupe, which are hazardous. They're small and they are vegetated. So they pose a challenge to detection of any signal, but still there is some displacement detected by GNSS, but apparently not visible on INSAR. So maybe we should not forget about not white swath, but small swath. And long wavelength, that may be less sensitive to displacement, but less sensitive to vegetation too.
So L-band.
L-band, yeah.
Rosa, is that?
But also a resolution issue as well.
Yes, yeah.
Also, yeah, many satellites now can go to meter or below, but those are not required globally. Yeah, one thing that I'd like to add onto that is for this like global, all these global studies, for a lot of these cases, they're still using a over 20-year-old DEM to process these. And I think that for a lot of these cases, when we need the high resolution, we should also very much have better and more up-to-date DEMs to accompany those. Yeah, hopefully Harmony will fix those issues. Yes.
Hey, while we're on the topic of harmony and DEMS anyway, I brought this up earlier with over a coffee, but I thought I'd mention it now as well. So these DEMS, if we talk about the commercial options that are available, for example, from GeoServe, they produce these high-res DEMs, but then they spend around 8 hours per high-res DEM to clear up any artifacts and issues with those DEMs. So you have a good quality DEM that you can actually use for INSAR processing, which of course is not realistic when you are producing like over whole regions like the Harmony mission will. So the alternative that is being proposed at the moment is of course to mask out areas of noise. But then what you're going to do is you're going to have these areas of incoherence of masked areas changing for every acquisition. So then we're going to need some method of stacking or combining these different acquired DEMs over the time period to actually get usable DEMs for INSAR. Because as we see here, I think a lot of work goes into the let's say the dike modeling, the volcanic side, but it's relatively harder to actually really kind of like process the INSAR data on a very kind of strong level. So having consistent, good quality DEMs that can be used out of the box by the volcano community, I think will add a lot more value. So finding ways to fill these masks that is not just interpolation, because that will create other issues. You can't just layer the Harmony mask on top of, say, the Glow 30 mask, because then you're going to get edge artifacts, which are going to create DEM errors. So this really needs to be kind of be taken into consideration how we deal with this masking, so that you actually get a useful DEM for INSAR.
And does someone who's connected to the Harmony mission want to reply to that?
I'm really trying to, yeah.
It's not just you.
Would say absolutely. And I guess what we've been focusing on is the time series of DEMs, where actually some of those issues probably aren't so important. But if you're thinking about a DEM for processing, but to make that DEM for processing, we would be able to use the whole year, probably 2 years of the mission of DEMs, and absolutely then you can start to use stacking, etc. To do that. And DLR are really the experts in doing that. I don't think that is a problem, but it's certainly something we should request so they know it's a product we want to them. We need something we really care about.
And it's definitely a priority for volcanoes.
Yeah. We need to make it a priority, but I don't think there's a problem.
And
Is the global DM still in there? Involvement is question about what we did. There wasn't very information.
Okay. As far as I know, but maybe not. I missed.
I remember.
The window. I couldn't miss this conversation.
Yeah, I think it was a while back, but yeah, there was a discussion at some point about whether the global, because I mean, Harmony is not going to be global coverage, of course, generally. So to make a global DM, it would have to be an extra requirement to so I've got a feeling it was dropped. But
Okay. All right. Sorry, I'm out of date.
well, maybe it's back in. I don't know.
No, I think you're probably right. Okay. Apologies, I've been on maternity leave, so I missed a whole chunk of the conversation.
But I mean, but maybe this is a recommendation.
Yeah, that's also what I think.
Yeah.
We didn't hear
Yeah.
But I think it's just very clear that we need it also.
But I guess one question I have is, to what extent will Harmony be giving people, like, here's the data, do your own DEM, versus here's a finished product? Because with INSAR missions, it was kind of, here's the raw data, and then people would do their interferograms, develop techniques for improving things and wrapping. All that stuff was kind of left to the science community or engineering community to develop those add-on techniques to actually get usable data. So,
yeah, my understanding is level 3 products. That's the plan, right? So actual, usable products.
On the other hand, it is an Earth Explorer rather than an operational mission, so they do want to make all the level 0, level 1 data available for scientists to do cool new things. Hopefully both.
I think that's right.
Okay, so we're kind of close to the allotted time for this. Does anyone have anything else that we should, any other topics we haven't covered that we should add in quickly?
So regarding what I said earlier, so just put something in, need 1 day I time series to develop or similar to develop multi-sensor machine learning algorithms.
Yeah, I mean, maybe it could just be worded differently. You don't have to mention machine learning because then people indeed stuff, yeah. But actually being able to deal with, sort of fire hose of data coming in. It's important, I guess.
So I think that's currently covered by 3 different points.
Sorry?
It's currently covered by 3 different points, but rest assured we are going to go back and consolidate this. This is just my notes. Yeah, these are my notes. We will tidy it up, I promise.
There's another point there about benchmarking. I don't know if anyone wants to, do you want to add anything about that, Fabien?
Yes, I think it's a discussion that we had in the past to have just some benchmarking. And I'm wondering if, like with different groups are developing anomaly detection and on the time series, if we are like it's mature enough that we have a benchmarking case that we can test performance, especially when we were to compare like different, of course, methods that can be compared. But it can also be benchmarking for processing, for unwrapping. We were talking about unwrapping this earlier. So yeah, I don't know your thought about trying to find benchmarking test site and have for comparison.
So in the past, I guess the ESA have funded into comparison studies like terra firma in the MBSAT days, basically into comparison studies. So that could be a recommendation that they ought, they ought to be funding an into comparison study. Yeah.
I mean, if it's, it won't, yeah, directly recommending things for ESA to fund. Come up with lots. I was going to say this issue of a kind of constellation approach to machine learning, or to, that might be something that ESA could support in terms of building up the data set.
Yeah.
Okay, unless there's anything else that's burning, I think we should probably wrap it up to give people time to go back to hotels, get dinner and everything. But if you do think of anything that you want to add in, please email one of us. And Fabian's going to present this on Friday, and things can be added till then. And thank you. And thank you for everyone who contributed.
Yeah.
And see you at the posters.
I noticed when you showed your Bermuda countries, the amplitude was about half of what I've heard. Now, are you doing any kind of atmospheric?
No.
I know once I did, I running mint.
I don't remember what you.
I'll put in, see what happens if I put in estimate a triple correlate atmosphere, and it reduced it, from 70 down to 30. Okay, it's throwing out a lot.
Well, the answer is no. The answer is either quick machine learning expenses, they're not properly in the way that you would. I don't really know about lawyers, we're good at that, and the summer to summer, getting those really makes a difference. As I'm sure you know, that we haven't really. If you look at Sierra Negra, also the really big deformation signal that occurred during the time of the eruption gets completely alien.
Yeah, I know that. I noticed for sure. Yeah.
It gets, and it doesn't know what to do. It can't unwrap it. So the time series just skips over it. So the point is, we know the time series are perfect. The point is not to make them.
Yeah.
But obviously the point is eventually to make them perfect. Yeah, no, it's definitely up.
All right.
My written benchmarking study needs to be done centrally in G20.
Tomorrow morning. Yeah, so I'll come up with the
Yes.
So come here it's starting like 9:20. It's in here and and conference auditorium. Conference auditorium 9. Okay, so I'll come here. 1 and 2. Yeah. 9 o'clock. I'll come here first. If everything is okay, I'll come to this place. I think it's okay. Yeah, I'm sure. But, double checking, making sure. No. Okay. Have a good evening. Yeah. Okay, nice.
I just yawned.